For centuries, humankind has gazed up at the night sky, mesmerized by its mysteries. From the shimmering glow of distant galaxies to the eerie silence of black holes, our cosmos consists of so much we have yet to understand. Join us as we'll venture into the unknown, explore otherworldly planets, and delve into the secrets of parallel universes. Neutron stars are among the universe's most extraordinary phenomena, and they emerge from the remnants of massive stars gone supernova. When a star with a mass between 8 to 20 times that of our Sun expends its nuclear fuel, it collapses under its gravity, stripping protons and electrons apart to form neutrons. The result is a celestial core that is an astonishingly dense sphere of neutrons, often just 12 miles in diameter, about the size of a small city, but packing in a mass greater than that of our Sun. To put it in perspective, a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. This extreme density bends the fabric of space-time in unusual ways, making neutron stars laboratories for studying the limits of physical laws. What makes neutron stars even stranger is their magnetic fields, which can be 1 trillion times stronger than Earth's magnetic field. This intense magnetism gives rise to pulsars, neutron stars that emit beams of electromagnetic radiation from their magnetic poles. Rotating at incredible speeds, sometimes hundreds of times per second, these pulsars act like cosmic lighthouses, their beams sweeping across space and detectable here on Earth as regular, precise pulses of radio waves. The interplay of extreme gravity, rapid rotation, and intense magnetism in neutron stars creates conditions so extreme they're almost impossible to replicate on Earth, captivating scientists and making them key objects of study in the quest to understand the fundamental properties of matter and the nature of the universe itself. Black holes form from the catastrophic death of massive stars, typically those with a mass at least 20 times greater than our Sun. As these stars reach the end of their life cycles, they exhaust their nuclear fuel and can no longer support themselves against the force of gravity. This triggers a supernova explosion where the outer layers are blasted into space, while the core collapses in on itself to an infinitesimal point known as a singularity. At this singularity, density and gravity become infinite, and the known laws of physics cease to operate in their conventional forms. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape the overwhelming gravitational pull. This invisibility, combined with the event horizon's profound gravitational effects, makes black holes incredibly elusive and mysterious. What truly makes black holes one of the most baffling objects in the universe is the way they warp space and time. Albert Einstein's theory of general relativity posits that massive objects distort the fabric of space-time, and black holes represent the most extreme example of this phenomenon. Time itself slows down near a black hole, a process known as time dilation, which means that an observer near the event horizon would age much more slowly compared to someone farther away. The mysteries deepen further with phenomena like Hawking radiation, theoretical emissions that suggest black holes could eventually evaporate, posing intriguing questions about the nature of information and entropy. Moreover, the mergers of black holes send ripples through space-time in the form of gravitational waves, a recent discovery that opens new avenues for understanding the universe. These enigmatic properties and the extreme conditions around black holes make them pivotal in the quest to unravel the deepest cosmic mysteries. White dwarfs are the remnants of stars that were not quite massive enough to end their lives in a supernova explosion. When a star with a mass less than about 8 times that of our Sun exhausts its nuclear fuel, it sheds its outer layers, creating a beautiful planetary nebula. What remains is the core, which transforms into a white dwarf. Occupying a size similar to Earth but with a mass comparable to that of the Sun, a white dwarf is an incredibly dense object, where a single teaspoon of its material would weigh several tons on Earth. These stellar remnants shine faintly with residual heat, but generate no new energy. They gradually cool and fade over billions of years, eventually becoming cold, dark black dwarfs, a theoretical end state that the universe has not yet had time to produce. White dwarfs play a crucial role in our understanding of stellar evolution and the life cycle of stars. They represent the final evolutionary stage of most stars, including our Sun, offering a glimpse into the future of our solar system. These cosmic objects also give scientists invaluable insights into the properties of matter under extreme densities. In binary star systems, white dwarfs can draw material from their companion stars, leading to spectacular phenomena like novae, sudden, dramatic increases in brightness due to thermonuclear runaways on their surfaces. In some cases, if a white dwarf accumulates enough mass from a companion star, it can trigger a Type Ia supernova, an incredibly luminous explosion that serves as a vital standard candle for measuring cosmic distances and expanding our understanding of the universe's accelerating growth. Thus, despite their small size and dim light, white dwarfs are essential actors in the grand narrative of cosmic evolution. A quasar, or quasi-stellar object, is one of the most energetic and luminous objects in the universe, powered by supermassive black holes situated at the centers of distant galaxies. These black holes have masses ranging from millions to billions of times that of our Sun. As matter spirals into the black hole from the surrounding accretion disk, the gravitational forces generate immense friction and heat, causing the matter to emit extraordinarily high amounts of energy. This energy spans the entire electromagnetic spectrum, from radio waves to X-rays, and in many cases, quasars outshine entire galaxies, making them visible across vast cosmic distances. The mind-boggling energy output of a quasar is primarily due to the efficient conversion of gravitational energy into light energy. The infalling gas and dust are accelerated to near-light speeds as they approach the event horizon, resulting in extreme temperatures and the emission of radiation. Unlike normal stars, which convert only a fraction of their mass into energy through nuclear fusion, quasars can convert mass into energy with nearly 10% efficiency, explaining their incredible luminosity. Additionally, the jets of particles that are often ejected from the regions around quasars at relativistic speeds add to their energy, creating some of the brightest phenomena in the universe. This combination of factors not only makes quasars fascinating celestial objects, but also crucial probes for understanding the early universe, as they are typically found billions of light years away, providing us with a glimpse into the distant past. Pulsars are a type of neutron star, the incredibly dense remnants of massive stars that have ended their lives in supernova explosions. What sets pulsars apart is their rapid rotation and the emission of strong beams of electromagnetic radiation from their magnetic poles. As these neutron stars spin, their beams sweep across space, much like a lighthouse's beacon. If one of these beams crosses Earth, we detect it as regular, extremely precise pulses of radio waves, or in some cases, X-rays and gamma rays. These pulses occur with such consistency that pulsars are sometimes referred to as the universe's most accurate celestial clocks. The significance of pulsars in astronomy extends well beyond their role as cosmic timekeepers. Their remarkable regularity and the extreme conditions under which they exist provide astronomers with unique tools to test the fundamental laws of physics, including the theory of general relativity. For instance, the study of binary pulsars, where two neutron stars orbit each other, has helped confirm the existence of gravitational waves, ripples in the fabric of space-time predicted by Einstein. Furthermore, pulsars are invaluable in mapping the galaxy. The precise timing of their pulses allows astronomers to measure distances and probe the interstellar medium. In some cases, pulsars have even been used as a natural form of a GPS system for spacecraft. Their role as laboratories for extreme physics and their contributions to astronomical measurements make pulsars indispensable to our understanding of the universe. A magnetar is a special type of neutron star distinguished by its extremely powerful magnetic field, which is about 1,000 times stronger than that of a typical neutron star and up to a quadrillion times stronger than Earth's magnetic field. These magnetic fields are so intense that they can distort atoms and are capable of influencing chemical bonds at great distances. Magnetars are formed in much the same way as regular neutron stars from the supernova explosion of a massive star, but they develop unusually strong magnetic fields, either during their formation or through a dynamo process soon afterward, due to their rapid initial rotation and the movement of conductive plasma. The differences between magnetars and regular neutron stars are stark, both in their observed behavior and their underlying physics. One of the most dramatic manifestations of a magnetar's power is the phenomenon known as a starquake, which occurs when the crust of the magnetar suddenly cracks under magnetic stress. These starquakes release vast amounts of energy, sometimes as much as 100 million times more than the energy produced by the sun in a year, in the form of X-rays and gamma rays. This energy release can result in intense outbursts called soft gamma repeaters, SGRs, or anomalous X-ray pulsars, AXPs, phenomena unique to magnetars. These outbursts are so luminous that they can be detected across vast galactic distances. The extraordinary magnetic fields, coupled with their resulting unique behaviors, make magnetars not just fascinating objects of study, but also key to understanding the most extreme conditions in the universe. Rogue planets, also known as interstellar planets, are fascinating celestial bodies that drift through the galaxy without being tethered to any star. Unlike the planets in our solar system which orbit the sun, these cosmic wanderers travel independently through the vast expanse of space. Their origins can be as varied as they are intriguing. Some rogue planets might have formed around a star and were later ejected from their original orbits due to gravitational interactions with other planets or passing stars. Others may have formed in isolation within vast molecular clouds, never having the chance to become part of a stellar system. The ability of rogue planets to travel without a star is a testament to the complex gravitational dynamics that govern our universe. Once ejected or formed in such isolation, these planets move through space under the influence of galactic gravitational forces. Without the warmth and energy of a nearby star, their surfaces are likely to be incredibly cold, potentially turning any water they might carry into ice. However, some theories suggest that rogue planets could still sustain subsurface oceans, kept warm by geothermal activity or residual heat from their formation. These unique characteristics make rogue planets compelling subjects of study as they challenge our understanding of planetary formation and survival in the universe's diverse and often harsh environments. Hypervelocity stars are extraordinary celestial travelers that move through space at speeds much greater than typical stars in our galaxy. These speeds can be so high that they allow the stars to escape the gravitational pull of the Milky Way entirely. While the average star in our galaxy moves at around 200 kilometers per second, hypervelocity stars can reach velocities exceeding 1,000 kilometers per second. The origin of these high speeds lies in dramatic astrophysical events, often involving interactions with supermassive black holes. The leading theory for the formation of hypervelocity stars involves the supermassive black hole at the center of our galaxy, known as Sagittarius A star. When a binary star system, two stars orbiting a common center, strays too close to this black hole, the immense gravitational forces can tear the system apart. One star is captured by the black hole, while the other is slingshotted away at incredible velocities. Another possible mechanism is the interaction between stars and the explosive force of a supernova, where the death of a massive star can impart significant kinetic energy to a companion star, sending it hurtling through the galaxy. These incredible speeds not only make hypervelocity stars fascinating objects to study, but also provide insights into the dynamic and sometimes violent processes that shape our galaxy. By tracking their trajectories, astronomers can glean valuable information about the distribution of mass and the gravitational landscape of the Milky Way and other galaxies. The Oort cloud is an enigmatic and distant region of our solar system, believed to be a vast spherical shell surrounding the Sun and extending from about 2,000 times the Earth's distance from the Sun, known as astronomical units or AU, to potentially as far as 100,000 AU. This distant expanse is thought to be populated by icy bodies and cometary nuclei that were left over from the early formation of the solar system approximately 4.5 billion years ago. Though no direct observations of the Oort cloud have been made, its existence is inferred primarily from the behavior and trajectories of long-period comets, which are objects that take more than 200 years to complete an orbit around the Sun. The significance of the Oort cloud lies in its role as a reservoir for these long-period comets. When gravitational perturbations, such as those caused by passing stars or the galactic tide, the gravitational pull from the Milky Way itself, disturb the orbits of these icy bodies, they can be sent on long elliptical paths that bring them into the inner solar system. As these comets approach the Sun, they heat up and develop glowing comas and tails, becoming visible from Earth and providing astronomers with valuable data about the early solar system's composition and conditions. The Oort cloud thus acts as a time capsule, preserving ancient materials that can offer clues about the formation of the solar system and the processes that governed its early evolution. Moreover, understanding the Oort cloud helps scientists in studying similar structures around other stars, adding a broader perspective to the study of planetary systems across the galaxy. Cosmic strings, theoretical one-dimensional topological defects in the fabric of space-time, offer intriguing possibilities for understanding the universe. Predicted by certain theories of the early universe, such as those involving high-energy particle physics and cosmology, cosmic strings are thought to have formed during symmetry-breaking phase transitions shortly after the Big Bang. These transitions are akin to the formation of cracks when water freezes into ice. Despite their incredibly thin and elongated nature, cosmic strings are hypothesized to be immensely dense, with even a string a millimeter in diameter potentially weighing as much as Mount Everest. In terms of their significance, cosmic strings have some profound implications for cosmology and the large-scale structure of the universe. Because of their immense mass and energy, cosmic strings would exert significant gravitational forces capable of bending light and affecting the trajectories of nearby objects. This property makes them potential tools for studying gravitational lensing effects, where the string could act as a gravitational lens, magnifying and distorting the light from background objects. Furthermore, the dynamics of cosmic strings, such as their vibrations and interactions, are thought to generate gravitational waves, ripples in space-time that could provide new insights into the early universe's conditions. Although direct evidence for cosmic strings is yet to be found, they continue to be a subject of considerable interest and research. Theoretical models suggest they could help explain various cosmic phenomena, including the distribution of galaxies and the anisotropies observed in the cosmic microwave background radiation, the afterglow of the Big Bang. In this way, cosmic strings offer a tantalizing possibility that, if confirmed, would profoundly deepen our understanding of the universe's fundamental properties and its earliest moments. Parallel universes, often referred to as the multiverse, are a compelling and mind-bending concept suggesting that our universe might be just one of many, perhaps an infinite number, existing in vast, diverse realms of reality. These other universes could have different physical laws, constants, and even entirely different histories. The idea of parallel universes fits into several modern scientific theories, each offering a unique perspective on how such universes could exist and interact, if at all, with our own. One prominent framework for parallel universes comes from the field of cosmology and the theory of cosmic inflation. According to this theory, in the very early moments after the Big Bang, the universe underwent an exponential expansion. Some models of inflation suggest that this process could create pocket universes within a larger inflating space, each with its own distinct properties. This version of the multiverse is often called the bubble universe model. In the realm of quantum mechanics, the many worlds interpretation offers another fascinating angle. Proposed by physicist Hugh Everett in the 1950s, this theory posits that every quantum event generates a branching of the universe into multiple outcomes, each resulting in a separate parallel universe. For example, in one universe, a quantum particle might spin clockwise, while in another it spins counterclockwise. According to this interpretation, every possible outcome of every event creates a new universe, leading to a staggeringly vast multiverse. String theory, which seeks to unify general relativity and quantum mechanics, also suggests the possibility of parallel universes. The theory posits that our universe is one of many three-dimensional branes floating in a higher dimensional space. Interactions or collisions between these branes could potentially give rise to universes with different physical properties. While the idea of parallel universes remains speculative and is largely beyond the reach of current empirical validation, it has significant implications for our understanding of existence and reality. If proven, the multiverse would revolutionize our comprehension of the cosmos and our place within it, challenging the notion that our universe is the single, unique cradle of life and complexity. The concept of a multiverse posits that our universe is just one of many, potentially an infinite number, existing in a larger framework of multiple parallel universes. These alternate universes could vary widely in their physical properties, laws, and even dimensions. The idea of a multiverse finds roots in several theoretical domains of modern physics and cosmology, each with its distinct rationale and implications. One of the primary models comes from cosmology and the theory of cosmic inflation. According to this theory, the rapid exponential expansion that occurred fractionally after the Big Bang could have caused isolated regions to balloon into separate bubble universes. Each of these bubbles can have different properties and physical constants, depending on the specific conditions under which they formed. This scenario explains why our universe appears to be fine-tuned for life, suggesting that we might just happen to be in one of an infinite number of universes where conditions are suitable for our existence. In quantum mechanics, the many worlds interpretation offers another lens through which to view the multiverse. According to this interpretation, every quantum event that can happen does happen, but in different branches of reality. For example, every time a particle can take multiple paths, the universe splits into a myriad of parallel universes where each possibility is realized. This approach implies a constantly branching multiverse, where every conceivable outcome of every event happens in some universe. String theory, a highly mathematical framework aiming to unify general relativity and quantum mechanics, brings forward yet another perspective. This theory posits that our universe might be one of many three-dimensional branes existing in a higher dimensional space. Our universe could collide or interact with other branes, potentially giving rise to new universes with varying physical laws and constants. String theory's extra dimensions allow for a rich tapestry of multiverse possibilities. The concept of a multiverse stretches the boundaries of our understanding and challenges the notion that our universe is the unique theater of reality. While experimental evidence for parallel universes remains elusive, ongoing research and technological advancements could one day provide deeper insights into this grand and tantalizing framework, fundamentally altering our comprehension of existence and our place within the cosmos. The evidence supporting the existence of other universes, or the multiverse, remains largely circumstantial and theoretical, given that direct empirical verification is extremely challenging with our current technology and understanding. Nonetheless, several lines of indirect evidence and theoretical frameworks provide intriguing hints that a multiverse might be a plausible concept. One of the most compelling pieces of circumstantial evidence comes from cosmic inflation theory. This theory posits that in the moments following the Big Bang, the universe underwent an exponential expansion. Certain models of inflation suggest that different regions of space stopped inflating at different times, leading to the creation of isolated bubble universes with their own distinct properties. The fine-tuning of physical constants in our universe, conditions that seem incredibly improbable yet are necessary for life, can be more easily explained if many universes exist, each with different properties. In this scenario, it's not surprising that we inhabit a universe with conditions suitable for life. We could only exist in such a universe. Another intriguing hint comes from quantum mechanics, specifically the many worlds interpretation. This interpretation posits that every quantum event generates a branching universe where every possible outcome occurs. While this remains a theoretical framework without direct empirical support, quantum experiments demonstrating phenomena like superposition and entanglement align well with the many worlds interpretation, lending it some degree of credence. Gravitational waves and cosmic microwave background, CMB radiation, offer potential, albeit indirect, avenues for gathering evidence. For instance, collisions between our universe and other universes could leave detectable imprints in the CMB, a faint glow left over from the Big Bang. Anomalies or unexplained patterns in the CMB might hint at interactions with other universes, although no conclusive evidence has been found thus far. String theory also provides a mathematical foundation for the multiverse concept. This theory posits the existence of multiple dimensions and suggests that different branes or universes could exist within a higher dimensional space. While string theory is mathematically complex and remains unproven, it offers a coherent framework for the existence of multiple universes. While direct evidence remains elusive, the multiverse concept is supported by several theoretical frameworks and indirect hints. These include cosmic inflation, the many worlds interpretation of quantum mechanics, potential gravitational wave signatures, and the mathematical underpinnings of string theory. Ongoing research and technological advancements in observational cosmology and particle physics may one day provide more concrete evidence to either support or refute the existence of parallel universes. String theory is a prominent theoretical framework in modern physics that seeks to reconcile general relativity and quantum mechanics, two pillars of our understanding of the universe that otherwise seem fundamentally incompatible. The core idea of string theory is that the most basic building blocks of reality are one-dimensional strings rather than point-like particles. These strings vibrate at different frequencies, and their vibrational modes correspond to the various particles we observe in nature, such as electrons, quarks, and photons. However, the mathematical consistency of string theory requires the existence of extra spatial dimensions beyond the familiar three of length, width, and height. In its simplest formulations, string theory posits a 10-dimensional universe, 9 spatial dimensions, and 1 time dimension. More advanced versions, such as M-theory, propose an 11-dimensional framework, adding another spatial dimension. The extra dimensions are not easily observable. They are theorized to be compactified or curled up at extremely small scales, far beyond the reach of current experimental techniques. These compactified dimensions could take on intricate shapes known as Calabi-Yau manifolds, which profoundly influence the properties and behavior of strings, ultimately affecting the physical constants and laws in our observable three-dimensional space. The existence of multiple dimensions in string theory has compelling implications for the concept of a multiverse. Different configurations of the compactified dimensions could lead to a vast number of distinct vacua, each with unique physical properties and constants. This landscape of possible vacua, sometimes referred to as the string theory landscape, provides a natural mechanism for the existence of many different universes. Each of these universes could inhabit a different point in the landscape, leading to a multiverse where the laws of physics and fundamental constants vary. Moreover, the presence of extra dimensions paves the way for the idea of branes, short for membranes, which are multidimensional objects within the higher dimensional space. Our observable universe could be a three-dimensional brane residing within a higher dimensional bulk. Interactions or collisions between different branes could give rise to phenomena observable in our universe, such as cosmic inflation or even the Big Bang itself. These brane interactions suggest that other universes or branes could exist parallel to our own, each with distinct characteristics and properties. String theory suggests the existence of multiple dimensions through its fundamental requirement for mathematical consistency and its ability to unify the forces of nature. These extra dimensions provide a rich tapestry of possibilities, supporting the idea of a multiverse where each universe has its unique properties shaped by the configuration of these additional spatial dimensions. While direct evidence for these extra dimensions and parallel universes remains elusive, string theory offers a coherently structured and compelling framework that extends our understanding of reality far beyond the familiar confines of our three-dimensional world. The brane theory, a cornerstone of string theory, posits that our universe is not the only one existing in the great expanse of reality. With its roots in higher dimensional physics, it suggests that our three-dimensional world is a brane floating in a space of more dimensions, 10 or even 11 dimensions to be precise. Picture a brane as a vast, flexible sheet, much like a trampoline, where gravity and other fundamental forces can manifest and stretch across its surface. However, what makes this concept particularly mind-bending is the proposal that numerous such branes could exist and parallel each other, each representing a different universe with its own set of physical laws and constants. Interactions between these branes can be thought of as cosmic events of monumental significance. When two branes come into proximity or even collide, the energy released could be immense, potentially giving rise to new universes or dramatically influencing each other's properties. This tantalizing hypothesis offers a framework for understanding the Big Bang not as a unique, singular event, but as a consequence of such brane collisions. Scientific sources estimate that these interactions could occur on timescales that stretch billions, if not trillions of years, providing an almost eternal playground for creation and annihilation. If verified, brane theory could radically transform our comprehension of the multiverse, suggesting a reality far more intricate and interconnected than previously imagined. Quantum mechanics, the bewildering science governing the subatomic world, introduces the notion of multiple universes through the many worlds interpretation, MWI. According to this interpretation, every quantum event branches out into a multitude of outcomes, each realized in its own separate universe. This theory builds upon the perplexing concept of quantum superposition, where particles exist in multiple states simultaneously until observed. When a measurement is made, instead of a single outcome crystallizing into reality, MWI suggests that all possible outcomes actually happen, but in different parallel universes. Consider opening Schrödinger's cat's box. Within this framework, one universe emerges where the cat is alive and another where it is dead. These parallel universes might interact in ways we can scarcely fathom, but quantum mechanics suggests that they coexist, branching out ceaselessly with every quantum event. By transforming the act of observation from a singular deterministic event to a branching of possibilities, quantum mechanics allows for an endlessly rich tapestry of realities. Each universe would follow its unique trajectory, diverging more and more from its counterparts over time, creating an unimaginably vast multiverse birthed from the fabric of quantum mechanics itself. This idea, although mind-boggling, offers an intriguing explanation for some of the fundamental uncertainties and peculiarities inherent in quantum theory. The holographic principle, an audacious and revolutionary idea in theoretical physics, suggests that the entire universe can be described as a two-dimensional information structure painted on the cosmological horizon. This concept arises from string theory and black hole thermodynamics, specifically from the puzzling observation that the maximum amount of information, or entropy, contained in a region of space scales not with its volume but with its surface area. To imagine this, think of a hologram, a two-dimensional surface which is capable of producing a three-dimensional image. In a similar vein, our three-dimensional reality, along with time, might be a projection from a far-distant two-dimensional boundary. This principle challenges our fundamental understanding of reality by proposing that our perception of depth, space, and even the flow of time may be illusions, much like the immersive experience provided by a holographic display. It fundamentally alters how we think about the universe's most basic structure by suggesting that the volumes we traverse and the spaces we inhabit might all be encoded on a flat, two-dimensional surface. Such a radical shift in perspective implies that in some profound sense, the universe as we perceive it is a kind of cosmic mirage. This opens up new avenues in quantum gravity research, providing a framework that potentially unifies general relativity and quantum mechanics, diving deeper into the true fabric of reality and offering answers to some of the most persistent questions about the universe's nature. Scientists examine the cosmic microwave background, CMB, the afterglow from the Big Bang, to search for potential signs of other universes. The CMB is a faint electromagnetic radiation that fills the universe, providing a snapshot of the infant cosmos roughly 380,000 years after its birth. By studying the minute fluctuations and patterns in the CMB, researchers hope to detect anomalies that could hint at interactions between our universe and others. One of the key strategies involves looking for cold spots or unusual patterns in the CMB. These might be areas where the temperature is slightly lower or the distribution of radiation deviates from the norm. Some theories propose that such anomalies could be evidence of gravitational imprints left by other universes bumping into our own, akin to cosmic bruises from past collisions. For instance, scientists have scrutinized a particularly large and enigmatic cold spot in the CMB for clues that might support the multiverse theory. If these anomalies are proven to result from interactions with other universes, it could provide compelling evidence that our cosmos is just one of many in the vast multiverse, fundamentally altering our understanding of the universe's architecture and origins. The concept of baby universes emerges from theories in quantum cosmology and inflates our understanding of universe formation. According to this notion, baby universes are smaller, self-contained regions of space that bud off from a parent universe, much like bubbles forming within a froth. These nascent universes might originate in a number of speculative ways, with quantum fluctuations in spacetime and the dynamics of cosmic inflation playing a central role. Cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang, suggests that regions of space can become isolated due to extreme stretching. During this process, quantum fluctuations can lead to the creation of pockets of space that become causally disconnected from the parent universe. These pockets could then evolve into entirely new universes with their own distinct properties and physical laws. Such processes could be seeded by the energy fluctuations inherent in the quantum fabric of spacetime, or they might emerge from the quantum foam, a concept suggesting that spacetime itself has a bubbly, foamy structure at incredibly small scales. If this is indeed the case, our own universe could be one among a potentially infinite series of offspring universes, each growing and developing in its unique way within an ever-reproducing cosmic bubble bath. This theory not only broadens our understanding of universe formation, but also deepens the mystery of the ultimate multiverse. The theory of cosmic inflation, introduced by physicist Alan Guth in the early 1980s, posits that the universe underwent an exponential expansion within the first tiny fraction of a second after the Big Bang. This rapid inflationary period stretched space so enormously that it smoothed out any irregularities, laying the groundwork for the large-scale structure of the cosmos we observe today. However, one of the intriguing implications of this theory is the possibility of eternal inflation, which suggests that the inflationary process did not end uniformly for the entire cosmos, but continues in some regions while stopping in others. Eternal inflation leads to a scenario where different patches of spacetime experience inflation independently, effectively creating pocket or bubble universes. In this framework, our observable universe is merely one bubble among countless others, each carving out its own niche in the ever-expanding multiverse. These individual bubbles can grow and form independent universes, each with potentially different properties, physical constants, and even different dimensions. As inflation perpetuates at the edges of these bubbles, it continually generates new regions that might break off and become separate universes themselves, thus providing a natural mechanism for the constant birth of new, distinct universes. This cosmological model not only addresses some of the conundrums posed by the homogeneous and isotropic nature of our universe, but also sets the stage for a mind-expanding vista where our universe is just a small part of a larger multiverse populated with myriad other universes, each wandering through the endless cosmic sea shaped by the dynamics of eternal inflation. The Fermi paradox arises from a simple yet profound question posed by physicist Enrico Fermi. Where is everybody? Given the vast number of stars in our galaxy, many of which potentially host habitable planets, the paradox highlights the surprising absence of evidence for extraterrestrial civilizations despite high statistical likelihood. If intelligent life has arisen elsewhere in the universe, why haven't we detected any signs of it, whether through radio signals, spacecraft, or other forms of communication? Several intriguing solutions have been proposed to explain this cosmic silence. One possibility is the rare Earth hypothesis, which suggests that the conditions allowing for complex life are extraordinarily rare, making Earth an exceptional outlier in an otherwise barren galaxy. Another idea is the Great Filter theory, which posits that there is some critical barrier in the evolutionary timeline that is extremely difficult to cross. This filter might lie in our past, making us extremely lucky, or it might still be ahead of us, posing a potential existential threat. Some researchers propose the zoo hypothesis, speculating that more advanced civilizations deliberately avoid contact with Earth, observing us as if we were part of a cosmic nature reserve. Technological limitations could also play a role. Civilizations might use communication methods beyond our current understanding or detection capabilities, such as highly directional beams or quantum communications, which we have yet to master. Lastly, self-destruction could be a common fate for intelligent civilizations, where technological advancement leads to unavoidable self-annihilation before interstellar communication or travel becomes feasible. Each of these solutions stretches our imagination and tests the boundaries of our understanding, emphasizing the complexity and mystery surrounding our place in the cosmos. Dark matter is one of the most enigmatic components of our universe, constituting about 85% of all matter, yet remaining invisible and undetectable through direct observation. Unlike ordinary matter, which makes up everything from stars to humans and interacts with light and other forms of electromagnetic radiation, dark matter does not emit, absorb, or reflect light, making it completely transparent and largely undetectable with traditional telescopes. Its presence is inferred primarily through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The importance of dark matter comes into sharp focus when studying the rotational speeds of galaxies. Observations show that stars at the outer edges of galaxies rotate much faster than can be accounted for by the gravitational pull of the visible matter alone. This discrepancy suggests that there is a significant amount of unseen mass contributing to the gravitational force, a mass attributed to dark matter. Moreover, dark matter is critical to our understanding of cosmic evolution. It acts as the scaffolding for the formation of galaxies, clusters, and larger structures, influencing how matter clumped together in the early universe to create the complex web of galaxies we observe today. Additionally, dark matter is a cornerstone in cosmological models, such as the lambda cold dark matter (LCDM) model, which provides the best explanations for the observed anisotropies in the cosmic microwave background, the distribution of galaxies, and the evolution of large-scale structures. Without accounting for dark matter, our equations and models would fail to accurately describe these phenomena, leaving significant gaps in our understanding of the universe's past, present, and future. Thus, while dark matter remains a profound mystery, unraveling its secrets is crucial to piecing together the intricate puzzle of the cosmos. Dark energy is an equally mystifying component of the cosmos, making up approximately 70% of the universe's total energy content. Unlike dark matter, which exerts a gravitational pull, dark energy is thought to have a repulsive gravitational effect, driving the accelerated expansion of the universe. This concept was thrust into the spotlight in the late 1990s, when astronomers observing distant supernovae discovered that the universe's expansion is not just continuing, but is accelerating over time. Dark energy is often associated with the cosmological constant, a term Einstein originally introduced in his equations of general relativity to achieve a static universe but later discarded, calling it his biggest blunder after the discovery of the universe's expansion. Ironically, it turns out this cosmological constant might accurately describe dark energy's influence. It suggests that dark energy is a property of space itself, and as the universe expands, more of it comes into existence, driving further acceleration in a self-perpetuating cycle. This gives rise to a rather counterintuitive concept. Even as galaxies move further apart, the space between them isn't empty, but filled with this unseen, expansive force. The effects of dark energy profoundly alter our predictions about the universe's fate. If dark energy continues to dominate, it could lead to scenarios such as the Big Freeze, where galaxies drift farther apart until stars burn out, and the universe becomes a cold, dark, and desolate place. Alternately, variations in the properties of dark energy might produce other endgames, like the Big Rip, where the universe's expansion accelerates to the point of tearing apart all matter. Thus, while its exact nature remains one of the greatest puzzles in cosmology, understanding dark energy is essential for comprehending the universe's ultimate trajectory and the forces that shape its destiny. Albert Einstein's theory of relativity, which encompasses both the special and general theories, fundamentally revolutionized our understanding of time and space, discarding the notions of absolute time and space that had prevailed since Newton's era. Special relativity, introduced in 1905, posited that the laws of physics are the same for all observers moving at constant velocities relative to each other, and that the speed of light is constant in all inertial frames. This led to the mind-bending realization that time and space are not independent, static entities, but are interwoven into a single four-dimensional continuum known as space-time. One of the most profound implications of special relativity is time dilation, where time actually slows down for objects moving at speeds close to the speed of light relative to a stationary observer. This isn't just theoretical, it's been confirmed through precise experiments, such as observing the decay rates of fast-moving particles and synchronizing atomic clocks on airplanes. Space itself also contracts along the direction of motion when nearing light speed, a phenomenon known as length contraction. These effects are not just mathematical quirks but real physical changes, reshaping our conception of time and space as flexible entities rather than rigid frameworks. Then in 1915, Einstein's general relativity extended these ideas further by introducing the concept that gravity is not an external force acting at a distance, but rather a curvature of space-time caused by mass and energy. Large masses like planets and stars bend the fabric of space-time, creating what we perceive as gravitational attraction. This curvature affects the passage of time, leading to phenomena such as gravitational time dilation, where time runs slower in stronger gravitational fields. For example, time ticks more slowly near a planet than it does in empty space, far from any gravitational source. General relativity has been confirmed by many experiments and observations, such as the bending of light around massive objects, gravitational lensing, and the precise timing of signals from GPS satellites that must account for these relativistic effects to provide accurate positioning. Relativity has shown us that time and space are dynamic and interconnected, influenced by velocity and gravity, and profoundly woven into the very fabric of the universe. This new understanding extends our grasp of the cosmos, influencing everything from the collapse of stars into black holes to the expansion history of the universe, making relativity a cornerstone of modern physics. The simulation hypothesis is a provocative theory suggesting that our entire universe, including all its physical laws, complexities, and inhabitants, might be an artificial simulation, akin to an incredibly advanced computer program. Proposed in a formal philosophical context by Nick Bostrom in 2003, this hypothesis builds upon the exponential advancements in computing power, artificial intelligence, and virtual reality. Bostrom's argument hinges on the idea that if a civilization progresses to a point where it can create highly sophisticated simulations indistinguishable from reality, it's conceivable that numerous such simulations could be created. Consequently, the probability that we are living in the one base reality, as opposed to one of the myriad simulations, becomes statistically quite small. Several factors contribute to why some scientists and philosophers take the simulation hypothesis seriously. One compelling aspect is the rapid evolution of technology and the observable trend toward increasingly immersive virtual environments. From video games to virtual reality, the trajectory suggests that future computational systems could eventually simulate conscious experiences and entire worlds with great fidelity. Additionally, certain peculiarities in the fundamental constants of the universe and the extraordinary fine-tuning required for life have led some to ponder if these could be akin to design parameters set by a programmer rather than arbitrary perfections of natural law. Moreover, the nature of quantum mechanics adds another layer of intrigue. The phenomenon of quantum indeterminacy, where particles do not have defined states until observed, almost echoes computational efficiency techniques, where resources are only rendered when necessary. Some scientists argue that this could be interpreted as evidence of a simulated environment operating on principles akin to those used in rendering techniques in virtual worlds. Furthermore, the simulation hypothesis prompts deep philosophical and ethical questions about existence, consciousness, and the nature of reality, making it not only a topic of scientific curiosity but also of profound philosophical exploration. While the hypothesis remains speculative and to many a thought experiment rather than a testable scientific theory, it stimulates important discussions about the limits of human knowledge and the potential capabilities of future civilizations. It challenges us to rethink our place in the universe and to explore the fundamental building blocks of reality itself in new and imaginative ways. Time travel, a captivating concept often depicted in science fiction, also has intriguing theoretical foundations within modern physics, particularly in the realms of general relativity and quantum mechanics. In general relativity, Einstein's equations suggest the possibility of closed time-like curves, CTCs, which are paths in spacetime that loop back on themselves. In theory, these loops could allow an object to return to its own past, thus enabling time travel. Exotic solutions to these equations, such as rotating black holes, Kerr black holes, or wormholes, Einstein-Rosen bridges, have been proposed as potential mechanisms for time travel. Wormholes are hypothetical passages through spacetime that could create shortcuts between distant points in the universe. If a stable wormhole could be engineered or naturally occurring ones could be discovered, it might allow for travel between different points in time as well as space. The concept hinges on the ability to stabilize a wormhole's throat, which would require negative energy or exotic matter. Current physics does not yet provide a clear method to achieve or even confirm the existence of such materials, keeping wormholes in the speculative domain. Quantum mechanics, meanwhile, introduces its own set of perplexing possibilities. Some interpretations of quantum theory, such as the many worlds interpretation, suggest that every quantum event spawns new, parallel universes. This interpretation could, in theory, allow for a form of time travel where traveling to the past would result in branching into a different timeline rather than altering the original one. This avoids the classic paradoxes associated with time travel, such as the grandfather paradox, where a time traveler might prevent their own existence by altering the past. Despite these theoretical possibilities, enormous practical and theoretical challenges remain. Stabilizing wormholes or creating negative energy densities far exceeds our current technological and scientific capabilities. Moreover, the existence of closed, time-like curves and the consistent application of such scenarios within the framework of known physics are still highly speculative and controversial. While time travel remains an alluring concept supported by some exotic solutions in modern physics, translating these theories into observable, practical phenomena continues to be an elusive goal. Nevertheless, the study of these concepts pushes the boundaries of our understanding and invites profound questions about the nature of time and reality. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels through spacetime that connect two separate points, theoretically allowing for instantaneous travel or communication between them. Picture spacetime as a two-dimensional sheet of paper. A wormhole would be like folding the paper so that two distant points touch, creating a shortcut. This idea stems from solutions to Einstein's equations of general relativity, which describe how matter and energy warp the fabric of spacetime. In principle, traveling through a wormhole could enable faster-than-light (FTL) travel, as you would traverse the shortcut rather than the intervening space. For instance, if one mouth of a wormhole were near Earth and the other near a distant star, traveling through the wormhole would allow you to reach the star far quicker than light traveling through normal space. However, several significant challenges accompany this concept. First, the creation and stabilization of a wormhole would require exotic matter with negative energy density to prevent the wormhole from collapsing. Such matter has not been observed and remains a theoretical construct. Without it, any wormhole would likely pinch off and become non-traversable. Moreover, even if a stable wormhole could be engineered, the effects of relativity at play within the wormhole could introduce complex issues, such as causality violations. For example, one theoretical concern is that traveling through a wormhole could potentially lead to time travel, with all its associated paradoxes. For instance, arriving at a destination before departing or interacting with one's past self. These scenarios, while fascinating, challenge our current understanding of physics and causality. While wormholes are compelling as a theoretical means for faster-than-light travel and exploring the deeper fabric of spacetime, they currently remain in the realm of speculation. We have no empirical evidence or practical means to create or navigate such structures. Nevertheless, the study of wormholes continues to inspire both scientific inquiry and imagination, pushing the boundaries of how we conceive the universe and our place within it. The Drake equation, formulated by astrophysicist Frank Drake in 1961, serves as a foundational tool in the scientific quest to estimate the number of active, communicative extraterrestrial civilizations within our galaxy, the Milky Way. This equation offers a framework to quantify the likelihood and abundance of alien life based on several astrophysical and biological factors. Even though it is primarily a probabilistic model, Its true significance lies in structuring our thinking about the factors that govern the existence of extraterrestrial life and guiding the search for it. The Drake equation, which estimates the number of extraterrestrial civilizations we might communicate with in our galaxy, involves several key factors. First, it considers the average rate of star formation in our galaxy. Next, it looks at the fraction of those stars that have planetary systems. Then it examines the average number of planets per star that could potentially support life, followed by the fraction of those planets where life actually evolves. It also includes the fraction of planets with life where intelligent life arises and the fraction of civilizations that develop detectable technology such as radio communication. Finally, it takes into account the length of time such civilizations can communicate or their communicative lifespan. By breaking down the immense question of extraterrestrial civilizations into these specific, measurable components, the Drake equation converts speculation into a structured, scientific investigation. Each term of the equation encapsulates an area of research, whether it be the formation of stars, the discovery of exoplanets, or the study of life's origins and evolution, with researchers continually refining these estimates as new data arrives. For instance, the increasing detection of exoplanets, many within the habitable zones of their stars, boosts the values of the fraction of stars with planetary systems and the average number of planets per star that could potentially support life, hinting at a galaxy teeming with potentially life-supporting worlds. Furthermore, the Drake equation encourages interdisciplinary collaboration. Astrophysicists, biologists, planetary scientists, and technologists all contribute pieces to the puzzle, fostering a holistic approach to one of humanity's most profound questions: are we alone? While the equation does not yield an exact number of alien civilizations, its real power lies in highlighting gaps in our knowledge and directing scientific efforts in the search for extraterrestrial intelligence, SETI. Thus, the Drake equation remains a crucial, thought-provoking tool that not only quantifies our quest for cosmic company, but also underscores the interconnectedness of various scientific realms in the pursuit of understanding our place in the universe. The anthropic principle is a philosophical consideration that leverages the fact that we exist to explain certain properties of the universe. It essentially states that the universe's fundamental constants and laws are observed to take on values that allow for the existence of life, specifically intelligent life capable of observing and questioning the universe's properties. There are two primary forms of the anthropic principle: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The weak anthropic principle asserts that we can only observe the conditions that allow for our existence. Thus, the universe must have those properties compatible with the emergence of observers like us. This principle serves as a selection effect. Given a vast range of possible universes or regions within a multiverse, we happen to find ourselves in one where conditions are right for life because we could not exist in regions where they aren't. For example, the specific values of the fundamental constants, such as the gravitational constant, the charge of the electron, or the cosmological constant, seem finely tuned to support the complexity needed for atoms, stars, planets, and ultimately life. If these constants were slightly different, a life-supporting universe might not be possible. The strong anthropic principle goes further, positing that the universe must have the properties that make the emergence of intelligent life inevitable. This version suggests that the universe's fundamental laws and constants are not merely a happenstance, but are in some way predisposed to ensure the existence of consciousness. This interpretation borders on metaphysical or teleological arguments, proposing that the universe is in some way compelled to support life. Scientists use the anthropic principle to provide context for the extraordinary fine-tuning observed in the universe. For instance, the precise interplay of fundamental forces required to form stable atoms, and the specific conditions necessary for stars to forge heavy elements critical for life, are all flagged as anthropic coincidences. Some researchers apply the anthropic principle within the multiverse hypothesis, suggesting that if there are countless universes with varying physical laws and constants, it is not surprising that at least one, ours, has conditions perfectly suited to life. In such a scenario, the anthropic principle helps explain why we observe these unlikely conditions without invoking more speculative or teleological explanations. While the anthropic principle is not a scientific theory in itself, it provides a valuable heuristic framework, guiding scientists in asking why certain conditions prevail and whether they are necessary for our existence. It remains a profound tool for contemplating the deep questions at the intersection of cosmology, physics, and philosophy, urging us to reflect on whether the universe's life-friendly character is a fortunate accident or something more intrinsic. Imagine the universe not as a one-time event, but as a grand cosmic symphony playing in endless cycles. This is the essence of the Big Bounce theory, an intriguing alternative to the Big Bang. According to this hypothesis, the universe undergoes a rhythmic sequence of expansions and contractions. Picture an eternal dance where the cosmos reaches a point of maximum expansion and then begins to contract, eventually collapsing into a dense state akin to a big crunch, only to bounce back in a new cycle of expansion. This idea challenges the notion of a singular beginning, proposing instead that what we perceive as the Big Bang might just be the latest act in an infinite series of bounces. Scientific explanations supporting the Big Bounce draw from the realm of quantum mechanics and general relativity. When the universe contracts to an extremely small point, quantum effects could dominate, preventing a complete collapse into a singularity, essentially a point of infinite density and zero volume. Instead, these quantum effects could cause a rebound, setting off a new expansion phase. In numbers, if the universe's density reaches approximately 1 × 10 raised to the 30th grams per cubic centimeter, quantum gravitational effects could kick in. Think of it as a trampoline. The fabric of space-time stretches and bounces back, driven by its own tension and the quirky laws of quantum mechanics. The beauty of this theory lies in the cyclical nature of the universe, suggesting that our cosmic history may be but one chapter in an infinite, ever-repeating saga. Exoplanets are planets that exist outside our solar system, orbiting stars other than our Sun. These distant worlds come in an astonishing variety of sizes and compositions, ranging from gas giants similar to Jupiter to rocky, Earth-like planets where liquid water might pool on the surface. The idea of exoplanets captured human imagination long before they were confirmed, but it wasn't until 1992 that scientists detected the first exoplanet orbiting a pulsar, a type of neutron star. Since then, over 4,000 exoplanets have been discovered, further fueling our quest to understand the diversity of planetary systems in our galaxy. Detecting these elusive celestial bodies involves several ingenious methods. One of the most effective is the transit method, used famously by the Kepler space telescope. Here, astronomers monitor the light from a star and look for periodic dimming. When an exoplanet crosses in front of its star, it blocks a tiny fraction of the starlight, creating a telltale dip in the star's brightness. Another method is the radial velocity technique, which detects the gravitational tug an exoplanet exerts on its parent star. This wobble causes slight shifts in the star's spectral lines due to the Doppler effect, noticeable even if the exoplanet itself can't be seen directly. A third, though less common method is direct imaging, where astronomers use advanced telescopes equipped with coronagraphs to block out the star's light, allowing the faint glow of the exoplanet to be captured. Technologies like these have not only confirmed the existence of exoplanets, but have also begun to reveal their atmospheric compositions and potential for habitability, edging us closer to answering the age-old question: are we alone in the universe? A super-Earth is a type of exoplanet with a mass greater than that of our Earth, but significantly less than that of gas giants like Neptune and Uranus. These fascinating worlds often range between 1.5 to 10 times Earth's mass, and their radii can be up to twice Earth's diameter. While they are more massive, super-Earths can either be rocky like our planet or have thick atmospheres composed of hydrogen and helium. The term super-Earth doesn't imply that these planets are necessarily similar to Earth in terms of environment or habitability. It's all about size and mass. One of the most captivating aspects of super-Earths is their potential to host conditions conducive to life. Planets like these could have a variety of surface environments, from vast oceans to towering mountain ranges. Due to their larger mass, super-Earths could retain thicker atmospheres, which might lead to more significant greenhouse effects, potentially maintaining liquid water on the surface, a crucial ingredient for life as we know it. For example, the exoplanet HD 40,307G, found about 42 light-years from Earth, orbits within its star's habitable zone, the region where temperatures could allow for liquid water. Additionally, their greater gravitational pull might help to sustain robust magnetic fields, shielding the surface from harmful cosmic and solar radiation. By studying super-Earths, scientists hope to understand not just how planets form and evolve, but also the diversity of conditions that could harbor life, revealing more about where and how life might thrive in the cosmos. The discovery of water on other planets has profound implications for our understanding of the universe and the potential for life beyond Earth. Water is a fundamental building block of life as we know it, playing crucial roles in biological processes, from the cellular level to complex ecosystems. When astronomers find water, or evidence of it, on other worlds, it vastly increases the potential that these planets or moons could support life, either currently or in the past. This, in turn, fuels our ongoing quest to answer one of humanity's most profound questions. Are we alone in the universe? Water in its various forms has been detected in several surprising locations within our own solar system. For instance, beneath the icy crust of Jupiter's moon Europa lies a vast subsurface ocean. Similarly, Saturn's moon Enceladus exhibits geysers that spew water vapor into space, suggesting the presence of liquid water below its icy exterior. On Mars, traces of ancient river valleys, polar ice caps, and recurring slope lineae, dark streaks that appear to ebb and flow, indicate that liquid water once existed on its surface and may still do so under specific conditions. The presence of water broadens our understanding of where and how life might emerge, indicating that potentially habitable conditions could exist in a variety of planetary environments, some vastly different from Earth. Scientific missions that aim to explore these watery realms, like the Europa Clipper and future missions to Mars, carry the promise of groundbreaking discoveries, potentially shifting the paradigm of life in the cosmos from a cosmic rarity to a common occurrence. Hot Jupiters are a class of exoplanets that have rocked our understanding of planetary formation. These gas giants, similar in size to Jupiter, orbit extremely close to their parent stars, often within a few million miles, sometimes even closer than Mercury is to our Sun. What makes hot Jupiters so intriguing and challenging is how they defy traditional models of planetary formation, which typically position gas giants forming far from their stars in colder, more distant regions of the planetary disk, where ices can condense and accumulate substantial masses before capturing large amounts of hydrogen and helium. The existence of hot Jupiters suggests that planetary systems can undergo significant migration after formation. Several theories have been proposed to explain this phenomenon. One prevalent idea is that these planets formed in the outer regions of the disk and then migrated inwards due to interactions with the protoplanetary disk or through gravitational perturbations from other large bodies. This inward migration could happen over a span of tens of thousands to millions of years, a cosmic eye blink, resulting in their scorching orbits. Another hypothesis involves tidal interactions with the star that pull the planet closer over time. These scenarios necessitate a re-evaluation of planet formation models, highlighting the dynamic and chaotic nature of planetary systems. Discovering hot Jupiters has expanded our understanding of the diversity and complexity of planetary environments. The extreme conditions on these planets, where temperatures could exceed 2,000 degrees Celsius, offer a fascinating glimpse into atmospheric phenomena such as intense radiation chemistry and weather patterns far more extreme than any observed in our solar system. The study of hot Jupiters helps refine our models not just for distant exoplanetary systems, but also for understanding the potential fates of planets, including those in our own earthly neighborhood, across the broad expanse of the cosmos. The habitable zone, often referred to as the Goldilocks zone, is a specific region around a star where conditions might be just right for liquid water to exist on the surface of a planet, neither too hot nor too cold. This zone is critical in the search for life because water is essential for all known forms of life on Earth. The presence of liquid water provides a medium where biochemical reactions can take place, enabling the development and sustenance of living organisms. Consequently, when scientists seek potential life-supporting planets, they focus their efforts on finding worlds within this temperate range. The dimensions of a habitable zone vary depending on the type and size of the star. For instance, around a smaller, cooler star like a red dwarf, the habitable zone is much closer to the star, perhaps only a few million miles away. In contrast, for a larger, hotter star, this zone is farther out. Our solar system's habitable zone, for instance, spans a region that encompasses Earth but not much beyond it. By examining these zones, astronomers are able to target their search for potentially life-supporting exoplanets more effectively. Instruments like the Kepler Space Telescope and its successors have been deployed to identify such planets by examining the dimming of starlight as planets transit across their stars, and by detecting the gravitational wobbles these planets induce in their host stars. Finding planets within a habitable zone doesn't guarantee they are teeming with life, but it does significantly narrow the possibilities, enabling scientists to prioritize resources and technologies in exploring these promising worlds. For example, the discovery of Proxima Centauri b, an exoplanet residing within the habitable zone of the star closest to our solar system, has generated tremendous excitement. If we were to find signs of liquid water or even biomarkers, indicators of biological processes on such a planet, it would be a monumental step in our understanding of life's potential ubiquity in the universe. Thus, the concept of the habitable zone is a cornerstone in astrobiology, shaping our explorations and fueling our hopes of discovering extraterrestrial life. HD 189733b is a particularly unusual exoplanet that has captivated astronomers with its extreme and exotic characteristics. Located about 64 light-years from Earth in the constellation Vulpecula, this gas giant is classified as a hot Jupiter, meaning it orbits extremely close to its parent star. What makes HD 189733b stand out is its vivid blue color, similar to Earth's appearance from space. However, the striking similarity ends there. The deep azure hue is not due to oceans or skies, but rather the result of an atmosphere filled with silicate particles. These particles scatter blue light, giving the planet its intense coloration. But this isn't your typical weather pattern. It's one that belies an environment of fierce volatility and immense heat. The conditions on HD 189733b are nothing short of hellish. With temperatures soaring to around 1000 degrees Celsius, the atmosphere is a tumultuous mix of boiling chemicals. Gravitational interactions with its star result in incredibly strong winds that can reach speeds of up to 7,000 kilometers per hour, far exceeding any wind speeds found on Earth. Adding to this chaotic environment is the possibility of rain made of molten glass. Yes, on HD 189733b, it could rain sideways shards of glass, driven by those furious winds, creating a nightmarish scenario no human could survive. These extreme conditions offer valuable insights into atmospheric dynamics under severe heat and pressure, expanding our understanding of what planetary atmospheres can be like beyond the more moderate conditions of our solar system. Such discoveries are not merely fantastical, they help refine our models of atmospheric physics and chemistry. Observing HD 189733b has been possible due to advancements in telescopic technology and methods such as transmission spectroscopy, where scientists study starlight filtered through the planet's atmosphere during transits. These investigations reveal the chemical composition and even the weather patterns of distant worlds, pushing the boundaries of our knowledge about the universe and highlighting the diverse array of planetary environments that exist within our galaxy. Tidally locked planets are fascinating celestial objects where one side always faces their parent star, while the other side remains in perpetual darkness. This phenomenon arises due to gravitational forces that synchronize the rotation of the planet with its orbital period around the star. Essentially, the same side of the planet is continually exposed to stellar light, creating starkly contrasting environments between its day side and night side. An example from our own cosmic backyard is our moon, which is tidally locked to Earth, always showing us the same face. The implications of tidal locking for planets orbiting other stars are profound, particularly in terms of their habitability. On a tidally locked planet within a star's habitable zone, the day side might be blisteringly hot while the night side could be frigidly cold. However, the boundary between these extremes, known as the terminator line, could potentially harbor conditions suitable for life. Here, temperatures might be more moderate, allowing for the existence of liquid water, a critical ingredient for life as we understand it. The atmosphere can act as a heat distributor, potentially transferring warmth from the starlit side to the dark side, mitigating temperature extremes somewhat. Understanding tidally locked planets also enriches our grasp of climate systems and atmospheric dynamics under unique conditions. These planets provide a natural laboratory for examining how atmospheres behave when subjected to continuous stellar radiation on one side and chronic darkness on the other. For instance, strong winds could circulate heat, creating interesting weather patterns that differ vastly from those on Earth. Advancements in observational technology, such as those offered by the James Webb Space Telescope, allow scientists to scrutinize tidally locked exoplanets in great detail. By studying their atmospheric compositions and climates, we develop a more comprehensive picture of the diverse environments that can exist on planets beyond our solar system, broadening our horizons about where and how life might subsist in the universe. Diamond planets, also intriguing, known as carbon planets, are a theoretical class of exoplanets that speculate the existence of celestial bodies composed mainly of carbon-rich materials. The hypothesis behind these glittering worlds stems from the unique conditions they may have experienced during their formation. If a planet forms around a star with an unusually high carbon-to-oxygen ratio, the elements available in the protoplanetary disk could lead to a composition heavily dominated by carbides rather than silicates. Under tremendous pressures found in planetary interiors, these carbides could transform into crystalline forms of carbon, essentially creating planets with vast reserves of diamond. The concept of diamond planets stretches our imagination and challenges conventional ideas of planetary geochemistry. One widely discussed candidate is the exoplanet 55 Cancri E, located about 40 light-years away in the constellation Cancer. This planet orbits its parent star so closely that temperatures on its surface exceed 2,000 degrees Celsius. Given these extreme conditions and its mass and radius measurements, scientists speculate its interior could be rich in carbon. Combining such high temperatures with the right amount of pressure could facilitate the formation of diamond, potentially making up a significant portion of the planet's composition. The formation of such planets is believed to occur in carbon-rich environments starved of oxygen. In these scenarios, materials like silicon carbide and graphite could be more plentiful, ultimately crystallizing into diamond under the intense pressure beneath the planet's surface layers. Investigations into diamond planets not only provide fascinating hypotheses about the diversity of planetary formation, but also help refine models of stellar and planetary compositions. They open up new avenues for understanding how varying chemical ratios in protoplanetary disks influence the types of planets that can form, thereby expanding our understanding of the universe's myriad planetary possibilities. Studying the atmospheres of distant planets or exoplanets is an astonishing feat of modern science, accomplished through several innovative techniques. One of the most significant methods is transit spectroscopy. When an exoplanet passes in front of its host star, a phenomenon known as a transit, a portion of the star's light filters through the planet's atmosphere before reaching our telescopes. By examining the spectrum of this light, scientists can detect the unique fingerprints of various gases. Elements like hydrogen, helium, water vapor, methane, and even possible biomarkers like oxygen and ozone leave distinct absorption lines in the spectrum, allowing researchers to infer the atmospheric composition. Another pivotal technique is the radial velocity method, which, though primarily used to detect exoplanets, can also offer indirect clues about atmospheric dynamics. This method involves observing the gravitational wobble exerted by the planet on its star, causing slight shifts in the star's spectrum due to the Doppler effect. When combined with transit data, it provides a more comprehensive understanding of the planet's atmosphere and possible weather patterns. For instance, extreme heat on one side of a tidally locked planet could produce noticeable shifts in the radial velocity data, indicating high-velocity winds distributing heat around the planet. Direct imaging has also made strides, particularly with the development of advanced instruments like coronagraphs and starshades, which block out the bright starlight to reveal the faint glow of the planet. Once a planet is directly imaged, spectroscopy can be applied to the light it emits or reflects, offering insights into atmospheric components. Missions such as the James Webb Space Telescope, JWST, promise to revolutionize our knowledge in this area, with its highly sensitive instruments designed to study the atmospheres of exoplanets in unprecedented detail. These techniques collectively enhance our understanding of distant worlds, opening windows into their climate systems, weather patterns, and potential habitability. By deciphering the chemical compositions and physical conditions of exoplanetary atmospheres, scientists are able to draw comparisons and contrasts with Earth's atmosphere, ultimately enriching our search for life beyond our solar system. The discovery of a planet like Kepler 186f has profound implications, both scientifically and philosophically. Located around 500 light-years away in the constellation Cygnus, Kepler 186f is one of the first Earth-sized exoplanets found in the habitable zone of its parent star, where conditions might be just right for liquid water to exist on the surface. Scientifically, this discovery is a milestone because it expands the possibility that planets with environments similar to Earth might be more common than previously thought. Kepler 186f orbits an M-dwarf star, which is cooler and smaller than our Sun, yet provides just enough energy for the planet to potentially maintain temperate conditions, paving the way for further exploration of similar red dwarf systems. The existence of such a planet in the habitable zone significantly advances our understanding of planetary formation and the distribution of potentially habitable worlds across the galaxy. If Kepler 186f has a stable climate, a suitable atmosphere, and perhaps even liquid water, it could harbor life, or at least provide the conditions necessary for it to develop. This makes Kepler 186f an excellent candidate for future missions focused on atmospheric analysis and potential habitability. As our technological capabilities improve, instruments like the James Webb Space Telescope and upcoming space telescopes could analyze its atmosphere for biosignatures, chemical indicators of life such as oxygen, methane, or water vapor. Philosophically, discovering a planet like Kepler 186f invites us to reconsider our place in the universe. It challenges the notion that Earth is uniquely special, suggesting instead that there might be countless other worlds with the potential for life. The discovery underscores the importance of investing in scientific exploration and technology capable of scrutinizing such distant planets. Furthermore, it inspires a sense of cosmic connectedness and curiosity, driving humanity to seek deeper answers about life, existence, and our shared future in the universe. The potential discovery of even microbial life on a planet like Kepler 186f would be transformative, reshaping our understanding of biology and the prevalence of life beyond Earth. A starburst galaxy is a type of galaxy experiencing an exceptionally high rate of star formation compared to what is typically observed in other galaxies. In starburst galaxies, stars are being born at hundreds or even thousands of times the rate seen in a normal galaxy like our Milky Way. This frenetic activity often results in galaxies that are bright, chaotic, and full of young, hot stars, which emit copious amounts of ultraviolet light and contribute to the intense luminosity of these celestial objects. The high rate of star formation in a starburst galaxy is generally triggered by external or internal events that compress large amounts of gas and dust, the raw materials for star formation, into dense regions where gravity can take over to create new stars. One common cause is a galactic collision or close encounter, where the gravitational interactions between the galaxies involved can compress gas and trigger rapid star formation. As these galaxies merge, the environmental conditions become ripe for starbursts. For instance, the famous antennae galaxies are in the process of merging and experiencing starburst activity. Internally, starburst activity can also be driven by processes within the galaxy itself, such as the presence of a central bar that funnels gas into the core, or spiral arms that effectively compress gas clouds through density waves. These internal dynamics can lead to the rapid formation of stars in specific regions, further fueled by subsequent supernova explosions that also compress nearby gas clouds, perpetuating the starburst cycle. Studying starburst galaxies offers astronomers valuable insights into the processes that regulate star formation and the evolution of galaxies. These intense stellar nurseries often produce massive stars, which live short, brilliant lives and end in supernova, enriching the interstellar medium with heavier elements. Understanding starburst galaxies thus helps us comprehend the complex life cycle of galaxies, as well as the conditions that lead to the spectacular fireworks of star formation seen in the distant early universe. An active galactic nucleus, or AGN, is a region at the center of some galaxies that emits extraordinarily high amounts of energy across the entire electromagnetic spectrum, from radio waves to gamma rays. This immense output is far greater than the combined light from all the stars in the host galaxy, indicating that some other powerful process is at work. The primary engine behind an AGN is believed to be a supermassive black hole, millions to billions of times the mass of our Sun, accreting matter at its core. As gas, dust, and other materials spiral inward toward the black hole, they form an accretion disk. The intense gravitational forces and high velocities within this disk cause the material to heat up immensely, radiating vast amounts of energy. Scientists identify AGNs through several key observational signatures. One method is through the detection of highly energetic emissions, such as X-rays and ultraviolet light, emanating from the galaxy's core. Telescopes like the Chandra X-ray Observatory and the Hubble Space Telescope have been instrumental in identifying and studying these emissions. Another hallmark of AGNs is the presence of strong, broad emission lines in their spectra. These lines are produced by gas moving at high speeds in the vicinity of the accretion disk, which shifts and broadens due to the Doppler effect. Additionally, AGNs often exhibit jets of charged particles that are ejected at nearly the speed of light, perpendicular to the accretion disk. These jets can extend millions of light-years into space and are observable in radio wavelengths. The supermassive black hole and its accretion disk can also produce variability. The energy output can change dramatically over short timescales from days to years, owing to the dynamic nature of the accretion process. There are several subcategories of AGNs, including quasars, blazars, Seyfert galaxies, and radio galaxies, each with its own unique set of observable characteristics. For instance, quasars are among the brightest and most energetic objects in the universe, often visible across vast cosmic distances. By studying AGNs, scientists gain insights into the behavior of supermassive black holes, the dynamics of galactic evolution, and the processes that can influence entire galaxies, thus enhancing our understanding of the universe's energetic and often violent nature. A Seyfert galaxy is a type of active galactic nucleus, AGN, known for its exceptionally bright core and distinctive emission lines. Named after the American astronomer Carl Seyfert, who first identified them in 1943, Seyfert galaxies are among the most studied AGNs due to their relative proximity and luminosity. They are typically classified into two main types: Seyfert Type 1 galaxies, which exhibit broad and narrow emission lines, indicating the presence of both fast-moving and slower-moving gas around the nucleus, and Seyfert Type 2 galaxies, which display only narrow emission lines, suggesting an obscured view of the inner, faster-moving regions. These galaxies are significant for several reasons. Firstly, Seyfert galaxies provide crucial insights into the nature of supermassive black holes and their interactions with surrounding matter. The high-energy phenomena observed in Seyfert galaxies result from the accretion of matter onto the supermassive black hole at the galaxy's core. This process releases enormous amounts of energy across various wavelengths, from radio waves to X-rays, allowing astronomers to study extreme physical conditions and high-energy astrophysical processes. Moreover, Seyfert galaxies serve as a bridge in our understanding of the AGN phenomenon's broader landscape. Positioned in terms of luminosity between the more common, less active galaxies and the extremely luminous quasars, Seyfert galaxies offer a more accessible framework for studying AGN characteristics and behavior. Observations of Seyfert galaxies contribute to our comprehension of the life cycle of galaxies, shedding light on how black holes grow, how they affect their host galaxies, and the role they play in galactic evolution. For example, The study of Seyfert galaxies helps unravel the complex interactions between supermassive black holes and star formation in galaxies, giving us a clearer picture of the feedback mechanisms that can regulate galaxy growth and structure. Finally, studying Seyfert galaxies enriches our broader understanding of cosmic phenomena. These galaxies offer valuable clues about the processes that dominate the energetic universe, from the distribution and behavior of interstellar gas to the effects of intense gravitational fields. By observing and analyzing Seyfert galaxies, scientists gain a deeper appreciation of the diverse and dynamic nature of the cosmos, further illuminating the fundamental processes that govern it. A galaxy merger is a transformative event where two or more galaxies collide and coalesce to form a single, larger galaxy. These cosmic interactions are more common than one might think, and play a significant role in the evolutionary history of galaxies. Contrary to a chaotic crash, galaxy mergers typically unfold over millions or even billions of years, owing to the vast distances and immense timescales involved. During these mergers, the gravitational forces at play can drastically alter the shapes, structures, and star formation rates of the involved galaxies. The effects of a galaxy merger are numerous and far-reaching. One of the most immediate impacts is the gravitational perturbation of gas clouds within the merging galaxies. These perturbations can trigger intense starburst activity, where the rate of star formation dramatically increases. This is due to the compression of gas and dust, fostering conditions ripe for the birth of new stars. For example, the antennae galaxies, currently in the process of merging, exhibit spectacular regions of starburst activity, illuminating the night sky with brilliant young stars. Another significant outcome of galaxy mergers is the eventual alteration in the morphology of the galaxies involved. Spiral galaxies might transform into elliptical galaxies as the merger progresses, their spiral arms being disrupted and merged into a more homogeneous elliptical structure. Additionally, galaxy mergers can also lead to the growth of central supermassive black holes. As the galaxies interact, gas and other material can funnel toward the galactic centers, providing fuel for these black holes and potentially igniting active galactic nuclei, AGN, activity. One spectacular result of this process is the formation of tidal tails, long, stream-like features composed of stars and interstellar material pulled out from the galaxies due to gravitational forces. These tidal tails can stretch over vast distances and provide clues about the dynamics and history of the merger. Moreover, new dwarf galaxies can sometimes form from the material in these tails, contributing to the population of smaller galaxies within the larger system. Galaxy mergers are fundamental cosmic events that reshape the structure, composition, and life cycle of galaxies. They act as a mechanism for galaxy growth and evolution, sparking new avenues of star formation while also potentially quenching it in certain regions due to the expulsion or heating of gas. Understanding galaxy mergers is crucial for piecing together the history of the universe and the development of the myriad galaxy forms we observe today. Imagine looking at the night sky through a powerful telescope and coming across a celestial object that resembles a shimmering cosmic donut. This is a ring galaxy, a fascinating and relatively rare structure in the universe. One of the most well-known examples of a ring galaxy is the Cartwheel Galaxy, situated about 500 million light-years away in the constellation Sculptor. These galaxies capture our imagination because they deviate so strikingly from the typical spiral or elliptical shapes most of us are familiar with. Ring galaxies form through a dramatic cosmic event, the collision or close pass of a smaller galaxy through the disk of a larger galaxy. As the intruder galaxy zooms through, it creates a powerful gravitational ripple akin to a stone dropping into a pond, sending waves of stars, gas, and dust radiating outward. These rings, glowing brightly with blue clusters of young, hot stars, stand out against the deeper regions of older, redder stars, evidencing a burst of star formation. The inner region is often left relatively empty or with less dense star populations, thus giving the ring its distinctive donut-like appearance. The dynamic and somewhat violent creation of ring galaxies offers us thrilling glimpses into the high-energy processes that shape the cosmos. Deep within the cores of most, if not all, galaxies lurk supermassive black holes, titanic entities with masses ranging from millions to billions of times that of our Sun. These cosmic giants are invisible by nature, making them enigmas wrapped in gravitational mystery. But scientists have developed ingenious methods to study these colossal voids. They use observations of the gravitational effects exerted on nearby stars and gas clouds. When particles or matter get too close to a supermassive black hole, they're accelerated to mind-boggling speeds and heated to extreme temperatures, emitting intense radiation detectable even across vast interstellar distances. Another critical tool in the astronomer's arsenal is the use of X-ray and radio telescopes, such as the Chandra X-ray Observatory and the Very Large Array in New Mexico. These instruments can pick up the X-ray emissions generated by the accretion disks, a swirling maelstrom of matter being sucked into the black hole. Scientists also utilize data from observatories like the Event Horizon Telescope, which famously provided the first ever image of a black hole's event horizon in the galaxy M87. By studying the motions of stars orbiting close to the galactic center with precision instruments like the Hubble Space Telescope and adaptive optics-equipped ground-based telescopes, researchers can infer the black hole's mass and other properties. Through these meticulous observations and advanced technologies, we can peer into the heart of galaxies to unlock the secrets of these majestic yet menacing supermassive black holes. In the vast expanse of the universe, the discovery of the Great Attractor has added a profound layer of complexity to our understanding of cosmic structures and motions. This gravitational anomaly, located roughly 150 million light-years away in the direction of the constellations of Centaurus and Hydra, is a region of space where tens of thousands of galaxies appear to be drawn toward at high velocities. The significance of the Great Attractor lies in its sheer ability to influence an extensive swath of the observable universe, including our own Milky Way. Scientists initially unveiled the Great Attractor's existence by studying the peculiar velocities of galaxies, movements that couldn't be explained solely by the expansion of the universe. Galaxies in our local cosmic neighborhood, like our Milky Way and the Andromeda Galaxy, display an extra motion toward this mysterious region. The discovery has led scientists to speculate about immense structures and unknown forces lurking behind the zone of avoidance, an area obscured by the dense plane of the Milky Way. High-energy surveys using X-rays and infrared wavelengths, like those from the Parkes Radio Telescope and the Rosat X-ray satellite, have started to peel away this shroud, revealing enormous clusters of galaxies and vast amounts of dark matter. The Great Attractor challenges our comprehension of galactic dynamics and the large-scale structure of the universe, serving as a gravitational puzzle waiting to be unraveled by ever more advanced observational techniques. Ultra-diffuse galaxies, or UDGs, are among the most puzzling celestial objects discovered in recent years. These galaxies possess the ghostly appearance of faint smudges across the night sky, with masses and sizes comparable to more familiar galaxies, yet they are spread out so thinly that they resemble galactic shadows. First identified in significant numbers in the Coma cluster, UDGs challenge our traditional models of galaxy formation by defying the expected density and star distribution that typically characterize galaxies of their size. One of the primary challenges these diffuse galaxies pose to our understanding lies in their unexpectedly high dark matter content. Despite their low visible star count, UDGs often seem to be held together firmly by vast quantities of dark matter. This discovery leads scientists to reconsider the relationship between dark matter, baryonic matter, including stars and gas, and galaxy formation processes. The existence of UDGs also raises questions about the violent histories these galaxies might have undergone. Some theories suggest that these galaxies could be remnants stripped bare by tidal forces or the results of star formation processes that fizzled out prematurely. To study these enigmatic formations, astronomers employ deep sky surveys using advanced astronomical instruments like the Hubble Space Telescope and the Dragonfly Telephoto Array, which specializes in detecting low-surface brightness objects. The further we delve into the perplexing nature of UDGs, the more we are forced to refine our broader theories about what it takes to form and sustain a galaxy in our universe, highlighting an intricate interplay of dark matter, cosmic evolution, and galactic dynamics. The Sombrero Galaxy, officially known as Messier 104, stands out as one of the most visually striking and structurally intriguing galaxies in the universe. Located about 30 million light-years away in the constellation Virgo, the Sombrero Galaxy gets its name from its resemblance to a broad-brimmed hat, featuring a brilliantly bright central bulge and an unusually pronounced and sharply defined disk. This unique structure creates a silhouette that looks like a glowing halo flanked by a dark, wide brim, making it a favorite among both amateur and professional astronomers. What makes the Sombrero Galaxy particularly fascinating is its combination of characteristics from both spiral and elliptical galaxies. Its central bulge is exceptionally luminous and densely packed with older stars, similar to what you might find in elliptical galaxies. Encircling this bulge is a thin, flat disk that includes spiraling lanes of dust and younger stars, typical of spiral galaxies. This hybrid structure has led some astronomers to hypothesize that the Sombrero Galaxy could be the result of a cosmic merger or other dynamic processes. Moreover, at the very heart of this majestic galaxy resides a supermassive black hole with a mass estimated to be about 1 billion times that of our Sun, contributing to the intense brightness of its core. Scientists use a variety of tools to study this celestial marvel, including optical telescopes like the Hubble Space Telescope and infrared detections from the Spitzer Space Telescope. These observations have revealed intricate details of the galaxy's composition and structure, such as the high levels of dust that absorb and diffuse light, enhancing the dark, shadowy brim against the bright halo. The Sombrero Galaxy, with its blend of elegance and complexity, serves as a natural laboratory to deepen our understanding of galactic formation and evolution, enriching our appreciation for the diverse architectures the universe can create. Scientists classify galaxies using a system known as the Hubble sequence, or Hubble tuning fork, a method devised by the acclaimed astronomer Edwin Hubble in the 1920s. This classification is based on the visual appearance and structural features of galaxies and can be divided into 3 primary categories: elliptical, spiral, and irregular galaxies, with each category having further subdivisions. Elliptical galaxies are characterized by their smooth, featureless light profiles and range from nearly spherical, classified as E0, to highly elongated elliptical shapes, classified up to E7. These galaxies typically consist of older red stars and have very little interstellar gas and dust, suggesting minimal ongoing star formation. Spiral galaxies, perhaps the most recognizable category, are divided into 2 main types: ordinary spirals and barred spirals. Ordinary spiral galaxies, denoted as S, have a central bulge with spirally arranged arms extending outward. They are further classified based on the tightness of their spiral arms and the size of their central bulge, ranging from Say, with tight, closely wound arms and a large central bulge, to C, with loosely wound arms and a smaller bulge. Barred spiral galaxies, denoted as SB, feature a central bar-shaped structure from which the spiral arms emanate, and they follow a similar classification from SBA to SBC based on the same criteria. Irregular galaxies, denoted as IR, do not fit neatly into the categories of elliptical or spiral galaxies. They lack a definitive shape and often appear chaotic, with no central bulge or spiral arm structure. These galaxies are typically rich in gas and dust, resulting in active star formation. Due to their varied appearances, many irregular galaxies are further studied and categorized based on their individual characteristics. The Hubble sequence provides a framework that helps astronomers understand the variety and evolution of galaxies within the cosmos. By analyzing their shapes, sizes, stellar populations, and other properties, scientists can infer the history and future development of these vast cosmic structures, adding depth to our comprehension of the universe's grand tapestry. Fast radio bursts, often abbreviated as FRBs, are one of the most perplexing phenomena in modern astronomy. These are incredibly brief but extraordinarily powerful bursts of radio waves lasting only a few milliseconds. Despite their fleeting nature, an individual FRB can release as much energy in a millisecond as the Sun emits over several days. Since their first discovery in 2007, FRBs have intrigued and mystified astronomers due to their mysterious origins and the tremendous distances they appear to travel, often billions of light-years across the cosmos to reach Earth. The origins of FRBs are a subject of intense scientific debate. Some FRBs are one-time events, while others have been observed to repeat, adding layers of complexity to understanding their sources. Potential explanations span a wide range of astrophysical phenomena. Some scientists propose they could be products of catastrophic events, such as neutron-star collisions or black hole mergers, while others suggest they might be linked to highly magnetized neutron stars, known as magnetars, which emit bursts of radio waves through their intense magnetic fields. The repeating FRBs, on the other hand, hint at more complex mechanisms that might involve less destructive processes. To study FRBs, astronomers rely on an array of specialized radio telescopes and observatories, such as the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and the Australian Square Kilometre Array Pathfinder, ASCAP. These instruments are designed to scan large sections of the sky and capture these fleeting signals with high precision. The enigma of FRBs lies not just in their origins, but also in the extreme conditions required to produce such intense energy bursts over astronomical distances. Each new detection expands our understanding and sometimes adds to the mystery, urging scientists to refine existing theories or develop entirely new models to explain these extraordinary cosmic signals. The cosmic microwave background, or CMB, is often described as the afterglow of the Big Bang, the primordial light that fills the entire universe. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, this faint microwave radiation provides an astonishing glimpse into the infancy of the cosmos. The CMB permeates every corner of the universe and is a near-uniform background radiation with a temperature of approximately -270 degrees Celsius, just a few degrees above absolute zero. This faint glow is what's left from the era roughly 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into hydrogen atoms, allowing photons to travel freely through space. The study of the CMB has unveiled a trove of secrets about the universe's origins, composition, and development. One of the most vital revelations from the CMB comes in the form of tiny temperature fluctuations, imprinted as a minute variance in the background radiation. These fluctuations, measured with exquisite precision by instruments such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, correspond to the density variations that would eventually evolve into galaxies and large-scale structures we see today. By analyzing these small variations, scientists can infer critical parameters about the universe, including its age, shape, and the proportions of its fundamental components like dark matter and dark energy. Moreover, the polarization of the CMB light contains additional clues to the early universe. The patterns of polarization can give insights into the conditions and processes occurring in the first moments after the Big Bang, such as the theory of cosmic inflation, a rapid expansion that is believed to have shaped the large-scale structure of the cosmos. The CMB acts as a cosmic fossil, preserving the universe's baby picture and allowing astronomers to decode the history and fundamental properties of everything that exists. Gravitational waves are ripples in the fabric of spacetime, first predicted by Albert Einstein in his theory of general relativity. These waves are generated by some of the universe's most violent and energetic processes, such as the collision and merger of black holes, neutron-star collisions, or even the cataclysmic events of supernovas. Detected directly for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, gravitational waves have opened an entirely new window through which we can observe and understand the cosmos. Gravitational waves allow scientists to study phenomena that are invisible through traditional electromagnetic observations, light, radio waves, X-rays, etc. Traditional telescopes might miss or be unable to capture the subtleties of these events due to dust obscuration or the lack of light emission, but gravitational waves pass through matter undisturbed, carrying unattenuated information about their origins. For instance, when LIGO first detected gravitational waves, the source was the merger of two black holes about 400 million light-years away, an event that emitted no light or electromagnetic radiation detectable by conventional means, but sent ripples through space-time that could be measured. The detection of gravitational waves also yields critical insights into the nature of gravity itself. By studying the signals from these waves, scientists can test the predictions of general relativity in extreme conditions, such as around black holes, where gravitational forces are immense. Observing these waves strengthens our understanding of the fundamental laws governing the universe. Additionally, combining gravitational wave data with traditional observational methods, a practice known as multi-messenger astronomy, enables a richer and more nuanced picture of cosmic events. For example, the historic detection of both gravitational waves and gamma rays from a neutron star collision in 2017 has allowed scientists to study the mechanisms of heavy element formation, such as gold and platinum. Gravitational waves help us penetrate deep cosmic mysteries, offering insights into previously inaccessible realms and transforming our comprehension of the universe's most potent forces and dramatic events. The discovery of the Higgs boson in 2012, confirmed through experiments at the Large Hadron Collider, LHC, at CERN, marked a monumental milestone in the field of particle physics. The significance of this discovery lies primarily in its validation of the Standard Model, the theoretical framework that describes the fundamental particles and forces, except gravity, that constitute our universe. The Higgs boson, often referred to as the God particle, is a manifestation of the Higgs field, an invisible energy field that pervades the universe and is responsible for giving mass to other particles. Before the Higgs boson's discovery, the existence of the Higgs field was a theoretical necessity to explain why certain particles, such as the W and Z bosons, have mass while photons, particles of light, do not. According to the theory, particles interact with the Higgs field, and through this interaction, they acquire mass. The more they interact, the heavier they become. The confirmation of the Higgs boson validated this mechanism, providing the missing piece of the Standard Model puzzle and solidifying our understanding of how the universe fundamentally operates. The discovery also opened new avenues for exploring physics beyond the Standard Model. While the Standard Model has been remarkably successful in explaining many aspects of particle physics, it does not account for phenomena such as dark matter, dark energy, or gravity itself. The Higgs boson discovery has set the stage for researchers to explore these frontiers, using the LHC and other experimental setups to search for new particles and interactions. Understanding the properties of the Higgs boson in greater detail can offer clues about the unification of forces at high energy scales and potentially lead to insights into the very early universe moments after the Big Bang. The discovery of the Higgs boson not only validated a crucial component of the Standard Model, but also ignited a new era of inquiry, promising deeper insights into the universe's underlying structure and pointing the way toward new, not yet imagined realms of physics. Cosmic rays are highly energetic particles that originate from outer space and constantly bombard Earth, traveling at nearly the speed of light. First discovered in the early 20th century by physicist Victor Hess, these particles are mostly protons, but they can also include heavier atomic nuclei and electrons. The study of cosmic rays has revealed much about the high-energy environments and processes happening throughout the cosmos, as well as the impact of these particles on Earth's atmosphere and technology. The origins of cosmic rays are diverse and span a wide range of astrophysical phenomena. A considerable portion of cosmic rays is believed to come from our own galaxy, the Milky Way, where they are accelerated by shockwaves from supernova remnants, massive stars that have ended their lives in explosive deaths. These processes generate particles with energies reaching up to several billion electron volts. Other sources of cosmic rays are thought to be even more exotic and powerful, such as supermassive black holes at the centers of galaxies, regions of intense star formation, and gamma-ray bursts. Additionally, some of the highest energy cosmic rays, with energies exceeding even those produced in supernovae, likely originate from outside our galaxy, possibly from intergalactic phenomena or from other galaxies with active galactic nuclei. The study of cosmic rays involves detecting the secondary particles they create when they collide with Earth's atmosphere, producing cascades of particles known as air showers. Instruments such as balloon-borne detectors, ground-based arrays like the Pierre-Auger Observatory, and satellite missions like the Alpha Magnetic Spectrometer on the International Space Station capture these events. Through these observations, scientists gain insights into the fundamental processes that govern particle acceleration and cosmic ray propagation across vast cosmic distances. Cosmic rays also help in exploring fundamental questions in physics. They provide a natural laboratory for studying particle interactions at energy scales far beyond what current human-made accelerators like the Large Hadron Collider can achieve. Understanding cosmic rays also has practical implications, such as assessing the radiation hazards for astronauts on long-duration space missions and designing better shielding for spacecraft and electronics. Cosmic rays are a crucial component of our universe's high-energy physics, originating from some of the most dramatic and powerful events in the cosmos. Their study helps us understand both the astrophysical processes that generate them and the fundamental aspects of particle physics that govern their behavior. Scientists employ a diverse array of techniques to study the possibility of life on moons such as Europa, orbiting Jupiter, and Enceladus, orbiting Saturn. Both of these icy moons have stirred excitement in the scientific community due to compelling evidence suggesting they harbor subsurface oceans beneath their thick, icy crusts. These environments could potentially offer the conditions necessary for life as we know it. One of the primary methods scientists use to study these moons is through spacecraft missions. NASA's Galileo mission provided crucial observations of Europa, revealing its icy surface and magnetic field data suggesting the presence of a salty subsurface ocean. Similarly, the Cassini mission made spectacular discoveries about Enceladus, including the observation of geysers ejecting water vapor and ice particles from cracks in the surface known as tiger stripes. These plumes offer a direct window into the subsurface ocean, allowing spacecraft instruments to analyze the expelled material for organic molecules and other compounds that could be indicative of biological processes. Upcoming and planned missions promise to delve even deeper. NASA's Europa Clipper, set to launch in the 2020s, will perform detailed reconnaissance of Europa's ice shell and subsurface ocean. It will carry sophisticated instruments designed to measure the thickness of the ice, analyze the moon's surface composition, and probe the moon's habitability. The European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, will focus on detailed observations of Jupiter's moons, including Europa, to gather more data on the subsurface oceans and their potential for life. Scientific instruments used in these missions range from ice-penetrating radar and magnetometers to spectrometers capable of detecting organic compounds. These tools help identify the chemical makeup of the moon's surfaces and any emitted plumes, searching for vital elements and compounds like water, methane, and ammonia, which are essential for life. Another critical aspect of studying these moons involves simulations and laboratory experiments on Earth. Scientists replicate the extreme conditions found on these icy moons to understand how life could potentially survive and thrive. By simulating the chemical interactions and potential energy sources available in these subsurface oceans, researchers can gauge the feasibility of microbial life existing in these alien environments. In sum, the study of Europa and Enceladus involves a combination of sophisticated spacecraft missions, advanced scientific instrumentation, and terrestrial laboratory simulations. The ultimate goal is to determine whether these intriguing moons possess the environmental conditions necessary for life, potentially answering one of humanity's most profound questions: are we alone in the universe? Einstein rings are fascinating astronomical phenomena predicted by Albert Einstein's theory of general relativity. They occur when a massive object, such as a galaxy or a cluster of galaxies, lies precisely between a distant light source, like a quasar or a background galaxy, and the observer. This massive intervening object acts as a gravitational lens, bending the light from the source around it. When the alignment is nearly perfect, the bending results in the appearance of a ring of light, known as an Einstein ring, encircling the lensing object. The significance of Einstein rings extends beyond their visual splendor. They are powerful tools for astronomers to study distant objects and the massive lensing structures themselves. One profound application is the detailed mapping of dark matter. The light-bending effect of gravitational lensing depends solely on the mass of the intervening object, allowing scientists to infer the mass distribution of the lens, including the elusive dark matter. By analyzing the shape, size, and distortion of the Einstein rings, researchers can create detailed maps of dark matter, offering insights into its distribution and properties. Einstein rings are also valuable for magnifying and resolving details of very distant celestial objects that would otherwise be too faint or too small to study with current technology. The gravitational lensing effect amplifies the light from these distant sources, effectively turning the lensing galaxy or cluster into a powerful cosmic telescope. This magnification allows astronomers to observe the structure and composition of early galaxies, star-forming regions, and other astrophysical phenomena in much greater detail. Additionally, the study of Einstein rings can provide critical tests of general relativity on cosmic scales, verifying Einstein's predictions about how massive objects bend space-time. By comparing observational data with theoretical models, scientists can refine their understanding of gravity and its role in the universe. Einstein rings are not only visually stunning but also serve as essential scientific tools. They help map dark matter, magnify distant galaxies, and provide a robust test of gravitational theories, significantly enhancing our comprehension of the universe. The phenomenon of redshift is a cornerstone observational evidence for the expansion of the universe, a concept that has fundamentally transformed our understanding of cosmology. Redshift occurs when the wavelength of light from an object moving away from us is stretched, shifting the light toward the red end of the spectrum. This was first observed by astronomers in the early 20th century and has profound implications for the structure and dynamics of the universe. Edwin Hubble's groundbreaking work in the 1920s provided the first clear evidence of cosmic expansion. Hubble observed that distant galaxies exhibited redshifts in their spectral lines, indicating that they were moving away from us. Moreover, his observations revealed a linear relationship between the distance of galaxies and their redshift. The farther away a galaxy was, the faster it appeared to be receding. This relationship is encapsulated in what is now known as Hubble's law. The discovery implied that the universe was not static but expanding, with galaxies moving away from each other as space itself stretches. The redshift of light from galaxies is analogous to the Doppler effect, which occurs with sound waves. For instance, the pitch of a siren on a passing ambulance changes as it moves toward and then away from an observer. In the case of redshift, it is the wavelength of light that changes due to the relative motion between the observer and the light source. However, in the context of cosmic expansion, the redshift is interpreted not just as a motion through space, but as a consequence of the expansion of space itself. As the universe expands, the fabric of space-time stretches, causing the wavelength of traveling light to elongate. Recent observations from advanced telescopes and space missions have further corroborated and expanded upon Hubble's findings. Instruments like the Hubble Space Telescope and the Sloan Digital Sky Survey have measured the redshifts of thousands of galaxies, providing a detailed map of the universe's expansion history. These observations have also shown that the rate of expansion is not constant, but has been accelerating, driven by an unknown force termed dark energy. The phenomenon of redshift provides robust evidence for the expansion of the universe. By analyzing the light from distant galaxies, scientists can trace back in time to understand how the universe has evolved and will continue to evolve, offering crucial insights into the nature of the cosmos and its ultimate fate. The axis of evil in cosmology refers to a peculiar and controversial alignment observed in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. This term was coined humorously by cosmologists to describe an unexpected and unexplained feature that seemed to challenge the foundational cosmological principle of isotropy, which posits that the universe should appear the same in all directions on large scales. The controversy began when data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later corroborated by the Planck satellite highlighted an anomaly in the temperature fluctuations of the CMB. Specifically, these fluctuations displayed a preferred direction or alignment across the sky, rather than being completely random as the standard cosmological models predicted. This preferred direction appears to correlate with the plane of our solar system, the ecliptic, which is particularly puzzling because the CMB should be unrelated to local astronomical structures. The existence of this axis of evil has led to a significant amount of debate and scrutiny within the cosmological community for several reasons. First and foremost, The detection of such an alignment could imply a break in the cosmological principle, shaking the very foundations of our understanding of the universe. If the universe has a preferred direction, it challenges the assumption that the cosmos should look statistically identical in all directions. Several explanations have been proposed to account for this anomaly. Some suggest it could be a statistical fluke, an artifact of the data processing, or contamination from local sources within our solar system, such as the solar system's foreground radiation. Others have considered more exotic theories, including the possibility of new physics or features in the early universe that have left an imprint on the CMB. Despite extensive investigation, the axis of evil remains controversial due to the implications it holds for our cosmological models. If future data and analyses can definitively confirm or refute this anomaly, it could either reinforce the standard cosmological framework or prompt a paradigm shift in our understanding of the universe. The axis of evil represents an intriguing and contentious anomaly in the cosmic microwave background that challenges the assumed isotropy of the universe. Its resolution could have profound implications for cosmology, potentially altering our comprehension of the cosmos on its most fundamental level. Scientists use the concept of cosmic voids, vast expanses of nearly empty space scattered throughout the cosmos, to unravel the large-scale structure of the universe. These voids, which can be tens to hundreds of millions of light-years in diameter, serve as a counterpoint to the dense regions of galaxies, galaxy clusters, and filaments that compose the cosmic web. By mapping out these emptier regions, astronomers can gain insights into the distribution and dynamics of matter on the grandest scales. The gravity-induced motion of galaxies around these voids, for instance, helps scientists measure the universe's expansion rate and the impact of dark energy. When galaxies are pulled away from the voids, the speed and direction of their movements can provide critical data, indicating the influence of unseen cosmic forces and helping to refine our models of how the universe evolves. Furthermore, the study of cosmic voids offers a unique laboratory for understanding fundamental physics. Because these voids contain lower densities of matter, they act as pristine environments relatively untouched by the energetic processes that occur in denser regions. This makes them ideal for testing theories about dark matter, neutrino masses, and other exotic particles. By observing how light from distant objects bends or travels through these voids, a process known as gravitational lensing, scientists can infer properties of the elusive dark matter that permeates the universe. Therefore, cosmic voids not only provide a contrasting backdrop to the areas teeming with galaxies, but also hold clues about the hidden aspects of the universe's composition and the laws governing its behavior. Searching for extraterrestrial life involves an array of techniques that span across different fields of science, blending the precision of astronomic observation with the creativity of theoretical physics and the rigor of biology. One major method scientists use is the study of exoplanets, planets outside our solar system. By scrutinizing these distant worlds, particularly those residing in the so-called habitable zone where conditions might support liquid water, scientists can identify promising candidates for life. Instruments like the Kepler Space Telescope have discovered thousands of exoplanets by detecting the tiny dips in a star's brightness that occur when a planet transits in front of it. More recently, the James Webb Space Telescope, with its advanced spectroscopic capabilities, can analyze the atmospheres of these planets, searching for biosignatures such as oxygen, methane, or other molecules that could indicate biological processes. Another powerful approach is the search for technosignatures, signals or artifacts that might indicate the presence of advanced civilizations. Projects like SETI, Search for Extraterrestrial Intelligence, utilize massive radio telescopes to scan the skies for unusual, non-random patterns of radio waves that could be artificial in origin. The Breakthrough Listen initiative, one of the most comprehensive searches for alien communication, extends this search to include optical signals and other possible indicators of extraterrestrial technology. Scientists also explore our own solar system for signs of microbial life, employing robotic missions to places like Mars, Europa, and Enceladus. These bodies are intriguing targets because they harbor environments such as subsurface oceans or hydrothermal vents that could resemble the early Earth conditions where life first emerged. Using landers, rovers, and orbiters equipped with tools to detect organic molecules and other potential biomarkers, researchers are piecing together the puzzle of life's potential beyond our planet. Scientists rely on sophisticated techniques to analyze exoplanet atmospheres and search for signs of life, with one of the key methods being spectroscopy. Spectroscopy involves splitting light from a star-planet system into its component wavelengths, much like a prism breaks sunlight into a rainbow. When a planet transits in front of its host star, a fraction of the starlight filters through the planet's atmosphere before reaching Earth-based or space telescopes. Certain molecules in the atmosphere absorb specific wavelengths of light, leaving distinctive fingerprints or absorption lines in the spectrum. By studying these absorption features, scientists can determine the atmospheric composition of the exoplanet, identifying key gases like oxygen, methane, water vapor, and carbon dioxide, which are considered potential biosignatures depending on their concentrations and interactions. Advanced instruments such as the James Webb Space Telescope and ground-based observatories like the European Extremely Large Telescope significantly enhance these spectroscopic studies. These instruments not only capture light across various spectral bands, but also possess the sensitivity to analyze even faint signals from distant planets. Additionally, the use of high-resolution spectroscopy allows scientists to distinguish between different layers and regions in an exoplanet's atmosphere, providing a more detailed picture of its chemical makeup and possible cloud structures. Computer models play a crucial role as well, simulating different atmospheric scenarios to interpret the observed spectra accurately. By comparing observational data with these models, scientists can infer whether the chemical balances are consistent with processes we associate with life, such as photosynthesis or microbial activity. The combination of direct spectral data, advanced telescopes, and robust modeling forms a comprehensive approach for detecting potential life-supporting environments beyond our solar system. The WOW signal remains one of the most intriguing events in the search for extraterrestrial intelligence. Detected on August 15, 1977 by Dr. Jerry R. Amon using Ohio State University's Big Ear radio telescope, this narrowband radio signal stood out due to its unusual intensity and frequency. Lasting for 72 seconds, the signal's strength and the precise frequency of 1,420 megahertz, a part of the spectrum naturally emitted by hydrogen atoms, captured the attention of scientists. This frequency is of particular interest because it is considered a quiet spot in the radio spectrum, often referred to as the waterhole, where emissions from cosmic noise are minimal, making it an optimal band for interstellar communication. While the WOW signal never repeated, which makes it impossible to conduct follow-up observations to confirm its source, its significance lies in the tantalizing possibility that it could have been a sign of an extraterrestrial technology. The signal prompted a surge of interest and has been a point of reference for subsequent SETI, search for extraterrestrial intelligence efforts. It revealed that the universe might hold surprises that challenge our understanding and that we need to cautiously and systematically continue our search with advancing technology. The event also highlighted the limitations of our then current methods and opened up discussions about refining our techniques for detecting and identifying non-repetitive, short-lived astronomical phenomena. To this day, the WOW signal symbolizes the potential for groundbreaking discoveries that could forever alter our understanding of our place in the universe. SETI programs, or Search for Extraterrestrial Intelligence initiatives, operate by scanning the cosmos for signals that might indicate the presence of advanced civilizations. The core strategy involves using large radio telescopes to listen for non-random structured signals that stand out from the usual cosmic background noise. Organizations like the SETI Institute and projects such as Breakthrough Listen utilize facilities like the Arecibo Observatory before its collapse in 2020 and the Green Bank Telescope. These instruments are capable of sweeping vast regions of the sky across a wide range of frequencies, seeking anomalies that wouldn't naturally occur in the universe. The process starts with identifying candidate regions of the sky that either contain potentially habitable exoplanets or are located in parts of the galaxy deemed suitable for advanced life. The telescopes capture radio emissions from these areas, converting them into data that are meticulously analyzed using powerful algorithms and computer programs. The goal is to filter out background noise and synthetic earthly interference, which can complicate the search. In recent years, there's been an expansion into the search for other technosignatures, such as laser pulses or high-powered electromagnetic bursts, leveraging the capabilities of both ground-based optical telescopes and orbital observatories. So far, SETI programs have not detected any definitive signals from extraterrestrial civilizations. However, the search has not been in vain. Along the way, these efforts have led to significant advancements in technology, data analysis techniques, and our understanding of the universe. Notable maybes like the famous WOW signal spark continual improvements and re-evaluations of methodologies. Besides, in the process, SETI research has uncovered previously unknown natural astrophysical phenomena, contributing valuable knowledge to the field of radio astronomy. As our tools become more refined and our capability to monitor the skies improves, scientists continue to hope that one day they might intercept a message from the stars, changing our view of human existence forever. The discovery of microbial life on Mars would be a watershed moment in the field of astrobiology, profoundly reshaping our understanding of life's prevalence and adaptability in the universe. First and foremost, it would suggest that life is not unique to Earth, bolstering the hypothesis that life could emerge independently in a variety of cosmic environments. This would imply that the conditions necessary for life's genesis are not exceptionally rare. Instead, they might be somewhat common, dramatically increasing the likelihood that life exists elsewhere in the universe. On a scientific level, finding Martian microbes would open up new avenues for the study of biology. Could these life forms share a common ancestry with Earth life, possibly indicating past interplanetary transfer of organisms, perhaps via meteorites? Or would they represent a completely independent origin, providing an invaluable second data point for understanding the principles of life's chemistry? The latter scenario would be particularly revolutionary, giving us a broader framework to define what constitutes life and potentially identifying universal biological laws. Furthermore, studying Martian microbes could offer insights into extremophiles, organisms that survive in extreme conditions, thereby enriching our comprehension of life's resilience and versatility. Beyond the scientific and philosophical implications, the discovery could also impact future space exploration and human missions to Mars. Detecting life would necessitate stringent planetary protection protocols to avoid contamination, both forward and backward, with Earth life. It would also fuel considerations of how humanity should responsibly interact with Martian ecosystems. Ethically, we would need to debate our approach to exploring and potentially colonizing a planet that hosts indigenous life forms, ensuring that our actions do not harm these newly discovered ecosystems. Finding even the simplest microbial life on Mars would not just reveal that we're not alone, but it would also fundamentally change our approach to exploration, ethics, and our place in the universe. To determine the habitability of moons in our solar system, scientists evaluate a range of factors that could support life as we know it, focusing on the presence of liquid water, energy sources, and necessary chemical ingredients. First and foremost, the presence of subsurface oceans is a critical criterion. Moons like Europa, Enceladus, and Titan have garnered significant attention because of strong evidence suggesting they harbor vast oceans beneath their icy crusts. For instance, data from spacecraft like the Galileo orbiter, which studied Jupiter and its moons, and the Cassini mission, which explored Saturn's system, indicate that gravitational interactions generate tidal heating, keeping these subsurface oceans in a liquid state despite their frigid environments. Another essential aspect is the availability of energy sources that could drive chemical reactions essential for life. This energy might come from tidal heating, as seen on Europa and Enceladus, where gravitational interactions with their parent planets and neighboring moons create internal friction and heat. On Titan, energy may also come from chemical reactions involving complex organic molecules. Scientists use instruments like spectrometers to analyze the surface and atmospheric compositions of these moons, searching for compounds like hydrogen, methane, and ammonia, which could indicate active chemical processes. Additionally, missions to these moons often aim to detect biomarkers, substances that could signify the presence of life. For example, the Cassini spacecraft discovered plumes of water vapor and organic molecules erupting from Enceladus's south pole, hinting at hydrothermal vents on the ocean floor. These environments on Earth teem with life, suggesting that similar conditions elsewhere could be equally promising. Upcoming missions like NASA's Europa Clipper, set to launch in the near future, will carry out detailed reconnaissance of Europa's ice shell and subsurface ocean, aiming to assess its habitability more comprehensively. By combining observational data, geological models, laboratory simulations, and comparative studies of Earth's extreme environments, scientists methodically build the case for potential habitability on these intriguing celestial bodies. The concept of panspermia proposes that life, or at least the essential components of life, can be distributed throughout the universe via space dust, meteoroids, comets, asteroids, or even spacecraft. According to this hypothesis, life might not have originated independently on Earth, but rather arrived here from elsewhere in space, seeding our planet with the building blocks necessary for life to develop. There are several variants of panspermia, including lithopanspermia, which suggests life could travel between planets within a solar system via rocky debris, and radiopanspermia, which posits that microscopic life forms could be propelled across vast interstellar distances by radiation pressure. One of the intriguing aspects of panspermia is how it reshapes our understanding of the origin of life on Earth, suggesting a possibly cosmic root rather than a strictly terrestrial one. This concept finds some support in the discovery of extremophiles on Earth, organisms that can withstand extreme conditions such as intense radiation, vacuum, and freezing temperatures. These resilient life forms suggest that microbial life could potentially survive a journey through the harsh environment of space. Additionally, meteorites found on Earth have been shown to contain organic molecules, amino acids, and even primitive cellular structures, which are precursors to life. In laboratory simulations, scientists have demonstrated that these organic compounds can form and survive under the conditions expected in space. While panspermia does not explain how life originated initially, it extends the scope of inquiry to consider a broader cosmological context. Implicitly, it raises the possibility that life could be more common in the universe, distributed via natural cosmic processes. If proven, it would imply that planets and moons sharing similar conditions could potentially host life, having been seeded by the same interstellar sources. The study of panspermia encourages a more integrated cosmic perspective, pushing scientists to consider the interconnectivity of celestial bodies in fostering and spreading life. This, in turn, could guide future explorations and missions aimed at detecting life beyond Earth, focusing on both local and interplanetary surveys. The study of extremophiles, organisms that thrive in extreme conditions on Earth, provides crucial insights that significantly inform the search for extraterrestrial life. Extremophiles can survive in environments once thought to be inhospitable to life, such as hydrothermal vents on the ocean floor, acidic hot springs, polar ice caps, and deep within the Earth's crust. By understanding how these resilient organisms adapt and thrive under such harsh conditions, scientists can expand the criteria for habitable environments beyond the narrow constraints previously considered. Take, for instance, thermophiles that flourish in extremely high temperatures around hydrothermal vents, where temperatures can exceed 250 degrees Celsius. These environments are similar to those that might exist on moons like Europa and Enceladus, where hydrothermal activity is suspected to occur beneath their icy crusts. The discovery that life can exist without sunlight, relying instead on chemosynthesis, deriving energy from chemical reactions involving minerals, suggests that subsurface oceans on these moons could harbor similar life forms. Similarly, acidophiles and alkaliphiles, which live in highly acidic or alkaline conditions, compel scientists to consider planets and moons with extreme pH levels as potential habitats. Furthermore, the discovery of microorganisms that can survive high levels of radiation, known as radio-resistant extremophiles, provides a model for hypothetical life on planets or moons with weak or no magnetic fields, where radiation exposure is significant. This adaptability hints that life's building blocks might be far more versatile and tenacious than previously assumed, making the search for extraterrestrial life all the more promising. By studying extremophiles, scientists not only learn about the limits and possibilities within Earth's ecosystems, but they also develop new methodologies for detecting life in extreme environments. Techniques used to study extremophiles, such as genomic sequencing and biochemical analysis, can be adapted for missions to Mars, Europa, and beyond. These insights shape the design of instruments and experiments on space probes and rovers, equipping them to detect biosignatures or life forms that might be radically different from those on Earth. Extremophiles broaden our understanding of where and how to look for life, suggesting that the universe could be teeming with life in places we are only beginning to explore. The potential consequences of making contact with an advanced extraterrestrial civilization are vast and multifaceted, touching on scientific, philosophical, sociocultural, and even geopolitical dimensions. On the scientific front, such a discovery would be revolutionary, providing unprecedented insights into advanced technologies and potentially offering solutions to some of humanity's most pressing problems, such as energy production, medicine, and environmental sustainability. Advanced extraterrestrial technologies could leapfrog current scientific paradigms, ushering in a new era of innovation and understanding of the universe's intricacies. Philosophically, making contact with an advanced civilization would profoundly affect our perception of humanity's place in the cosmos. It would challenge long-held beliefs about our uniqueness and possibly even influence religious and existential perspectives. The realization that we are not alone could foster a sense of unity and shared destiny among Earth's inhabitants, encouraging global cooperation and peace. Conversely, it could also cause existential anxiety and cultural shocks as societies struggle to integrate this new reality with existing worldviews. Socioculturally, the implications would be equally transformative. Cultures and societies around the globe would likely experience shifts in their identity, values, and priorities. The knowledge that an advanced civilization exists would inevitably lead to comparisons, perhaps highlighting our strengths while also emphasizing areas where we lag behind. This could motivate humanity to aspire toward greater achievements, fostering scientific curiosity and collective progress. However, there could also be divisions and conflicts spurred by differing responses to this revelation, with some groups embracing the change and others resisting it. On a geopolitical level, the dynamics of power and international relations could be significantly altered. Nations might vie for leadership and control in dealings with the extraterrestrial civilization, leading to shifts in political alliances and potential conflicts. The knowledge and technologies gained could exacerbate or mitigate existing power disparities, depending on how they are shared and used. Policies and frameworks for international cooperation and communication would need to be developed and implemented to handle the complex and unprecedented interactions with an advanced extraterrestrial entity. In conclusion, the contact with an advanced extraterrestrial civilization would initiate a profound and multifaceted transformation across all aspects of human life, challenging us to rethink our place in the universe, our technological aspirations, and our social and political structures. It would be both an opportunity and a challenge, likely defining a new epoch in human history. Scientists have devised several methods to send messages to potential extraterrestrial civilizations, employing a range of technologies and frequencies to maximize the chances of detection. One of the most established approaches involves the use of powerful radio telescopes to transmit radio signals into space. Projects like the Arecibo message, sent in 1974 from the Arecibo Observatory in Puerto Rico, utilized this method to broadcast a binary encoded message containing basic information about humanity and our position in the solar system. These radio messages are carefully crafted in universal scientific language, utilizing mathematical and chemical principles that any technologically advanced civilization might understand. More recent initiatives such as the METI, Messaging Extraterrestrial Intelligence Program, aim to refine and expand these efforts. METI seeks not only to broadcast signals but to engage in a long-term project of periodic transmissions focused on specific star systems deemed likely to host habitable planets. They use higher frequency radio waves that can travel vast distances with minimal interference from cosmic noise. Additionally, METI plans often consider transmitting at the hydrogen line, 1420 MHz, a frequency naturally quiet and significant in astronomy, to increase the likelihood that extraterrestrial civilizations might be listening. Scientists are also exploring the potential of optical communication, using lasers to send pulses of light carrying information across interstellar distances. This method can transmit data at incredibly high rates and with great precision. Experiments have demonstrated that laser signals can be detected from hundreds of light-years away with current technology, promising a viable alternative or complement to radio waves. Projects like Breakthrough Starshot, part of the Breakthrough initiatives backed by investor Yuri Milner and physicist Stephen Hawking, aim to send small, light-propelled spacecraft to nearby star systems. These tiny spacecraft, equipped with cameras and sensors, would also carry laser communication systems to relay information back to Earth and potentially signal intelligent civilizations. As we devise and implement these methods, ethical considerations and international cooperation are crucial. Scientists widely agree that any decision to send messages should involve broad consultations and consensus, given the potential far-reaching consequences. Protocols are being developed to ensure that messages are constructed thoughtfully, representing humanity responsibly, and considering the potential risks and benefits of contacting extraterrestrial intelligence. The goal is not just to send messages into the void, but to embark on a responsible and coordinated effort to discover whether we are truly alone in the cosmos. Several upcoming missions in space exploration promise to significantly advance our understanding of the cosmos, exploring everything from the surface of the Moon to the outer reaches of our solar system and beyond. One of the most highly anticipated missions is NASA's Artemis program, which aims to return humans to the Moon by 2024 and establish a sustainable lunar presence. The Artemis missions will lay the groundwork for future human exploration of Mars by testing new technologies and conducting scientific research on the Moon's surface. Artemis also envisions the Lunar Gateway, a space station orbiting the Moon that will serve as a staging point for deeper space missions. Another exciting mission is the James Webb Space Telescope, JWST, set to launch in December 2021 after multiple delays. As the successor to the Hubble Space Telescope, JWST will offer unprecedented resolution and sensitivity in the infrared spectrum. Its primary goals include studying the formation of stars and planets, investigating the atmospheres of exoplanets for potential signs of life, and peering into the early universe to better understand galaxy formation and evolution. The data gathered by JWST could transform our understanding of some of the universe's most profound mysteries. Moving outward, NASA's Europa Clipper mission, planned for the mid-2020s, will conduct detailed reconnaissance of Jupiter's moon Europa. Europa is one of the most promising candidates for extraterrestrial life within our solar system, thanks to its subsurface ocean beneath an icy crust. The Europa Clipper will carry a suite of scientific instruments to analyze the moon's ice shell, composition, and potential habitability. By studying the plumes of water vapor detected emanating from Europa's surface, the mission hopes to assess the conditions within its hidden ocean. In the realm of interstellar exploration, the Breakthrough Starshot initiative aims to send tiny laser-driven spacecraft to the Alpha Centauri star system, our nearest stellar neighbor, within the next few decades. These star chips would travel at a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 20 years. Once there, they would capture images and gather data on any potentially habitable planets orbiting the stars in the system, sending this information back to Earth via laser communication. Lastly, Mars continues to be a focal point with missions like ESA's ExoMars rover, scheduled for launch in 2022, which will drill below the Martian surface in search of signs of past or present life. Similarly, NASA's Perseverance rover, having already landed on Mars in 2021, will collect samples for eventual return to Earth by future missions. These efforts are critical steps toward answering the fundamental question of whether life ever existed on Mars and preparing for future crewed missions to the Red Planet. Together, these ambitious missions highlight an exciting era of discovery and exploration that not only aims to expand our scientific knowledge, but also prepares humanity for future adventures beyond our home planet. Scientists have laid out comprehensive plans to explore the icy moons of Jupiter and Saturn, focusing on their potential to harbor subsurface oceans that could support life. Among these intriguing celestial bodies, Europa, Ganymede, and Enceladus are of particular interest. To investigate these moons, space agencies are developing a series of advanced missions equipped with sophisticated instruments designed to penetrate their icy crusts and gather crucial data. For Europa, NASA's Europa Clipper mission, set to launch in the mid-2020s, is one of the most highly anticipated endeavors. The Europa Clipper will conduct multiple flybys of Europa using a suite of instruments to assess the moon's habitability. Equipped with ice-penetrating radar, magnetometers, and spectrometers, the Clipper will map Europa's ice shell and search for subsurface lakes, measure the moon's magnetic field to infer the depth and salinity of its ocean, and analyze the composition of the plumes of water vapor detected erupting from its surface. The mission aims to understand the moon's geology, ice thickness, and the potential for hydrothermal activity on the ocean floor, which could constitute an energy source for life. In parallel, the European Space Agency, ESA, is preparing the Jupiter Icy Moons Explorer, JUICE, scheduled for launch in 2022. JUICE will perform detailed observations of Jupiter's moons Ganymede, Callisto, and Europa. Ganymede, the largest moon in the solar system, is of particular interest because it has its own magnetic field and a suspected subsurface ocean. JUICE will carry out 9 flybys of Ganymede before ultimately entering its orbit, using its instruments to study the moon's ice shell, magnetic environment, and potential signs of habitability. The spacecraft's suite of spectrometers, radar systems, and cameras will provide critical data on the moon's complex surface and interior structure. The exploration of Saturn's moons is equally ambitious, with Enceladus being a prime target due to its active geysers that spout water vapor and organic compounds from a subsurface ocean. NASA's Cassini mission, which ended in 2017, already provided invaluable data indicating hydrothermal processes on Enceladus's seafloor. Future missions currently under concept studies, such as Enceladus Life Finder, ELF, and Enceladus Orbilander, intend to follow up on these discoveries. These missions would involve orbiters designed to conduct flybys through Enceladus's plumes, equipped with mass spectrometers and other tools to analyze the ejected material for complex organic molecules and signs of microbial life. Additionally, Titan, Saturn's largest moon, has drawn attention with its methane lakes and rivers. NASA's Dragonfly mission, scheduled for launch in 2027, will send a rotorcraft lander to Titan's surface. Dragonfly will hop across various locations, sampling the moon's surface chemistry and atmospheric conditions, searching for prebiotic chemistry, and exploring the potential habitats for life. Through these meticulous and technologically advanced missions, scientists aim to uncover the secrets of these intriguing ice-covered worlds, assessing their potential to support life and deepening our understanding of the fundamental processes that shape our solar system's diverse environments. The quest to detect and study exoplanets, planets orbiting stars outside our solar system, has driven significant technological advancements in astronomy. One of the foremost technologies is the development of more sensitive and precise space telescopes. The James Webb Space Telescope, JWST, set to launch in December 2021, is expected to revolutionize exoplanet detection and characterization with its advanced infrared capabilities. JWST's instruments can observe exoplanets as they transit their host stars, capturing the starlight that filters through their atmospheres. This allows scientists to analyze the atmospheric composition and search for potential biosignatures such as water vapor, methane, and other organic molecules. Another groundbreaking project is the Transiting Exoplanet Survey Satellite, TESS, which was launched in 2018. TESS employs a wide field array of cameras to monitor over 85% of the sky, specifically targeting the brightest stars. By observing periodic dips in brightness caused by planets transiting in front of their stars, TESS can identify thousands of potential exoplanets, particularly focusing on Earth-sized and super-Earth-sized planets in the habitable zones of their stars. Ground-based telescopes are also undergoing significant upgrades to enhance exoplanet detection capabilities. The Extremely Large Telescope, ELT, currently under construction in Chile, will feature a 39-meter primary mirror, making it the largest optical telescope in the world upon completion. ELT will employ adaptive optics technology to correct for atmospheric distortions, enabling it to achieve unprecedented resolution and sensitivity. This will allow it to directly image exoplanets and study their atmospheres in detail. Similarly, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will provide complementary capabilities, focusing on high-resolution spectroscopy to analyze exoplanetary atmospheres and surface conditions. Advanced spectrographs, such as the Echelle spectrograph for rocky exoplanet and stable spectroscopic observations, ESPRESSO, on the Very Large Telescope, VLT, in Chile, are also crucial in improving our detection abilities. ESPRESSO can measure the minute wobbles in a star's motion caused by the gravitational pull of orbiting planets, a method known as the radial velocity technique. This high precision allows for the detection of smaller Earth-sized exoplanets and the characterization of their mass and orbits. Additionally, innovative techniques like the use of star shades, spacecraft that block out a star's light to reveal its orbiting planets, are being developed. NASA's planned mission, known as the Starshade Rendezvous, aims to deploy a large, sunflower-shaped spacecraft to work in tandem with space telescopes like the Nancy Grace Roman Space Telescope, formerly WFIRST. This combination will enhance direct imaging capabilities, allowing scientists to photograph and study the light reflected off exoplanets directly, even in the glare of their parent stars. These cutting-edge technologies and instruments collectively push the boundaries of our ability to detect and characterize exoplanets. They not only enhance our understanding of planetary systems, but also bring us closer to answering the profound question of whether we are alone in the universe. Through detailed observations and sophisticated analyses, scientists aim to discover more about the diverse worlds orbiting other stars, potentially uncovering environments that could support life. The James Webb Space Telescope, JWST, promises to revolutionize our understanding of the universe across multiple fronts, thanks to its advanced design and capabilities that far surpass those of its predecessors, such as the Hubble Space Telescope. One of the key features enabling this leap is JWST's powerful infrared observation capabilities, housed within its 6.5-meter primary mirror and shielded from the sun's heat by an expansive sunshield. This allows JWST to look deeper into space and further back in time than ever before. Firstly, JWST will profoundly enhance our understanding of the early universe. By observing the redshifted light from the first galaxies that formed after the Big Bang, JWST aims to capture images and data from when the universe was only a few 100 million years old. This will provide invaluable insights into the formation and evolution of the earliest stars and galaxies, shedding light on the cosmic dawn and the processes that have shaped the large-scale structure of the universe over billions of years. By studying these ancient celestial objects, scientists hope to answer fundamental questions about the nature of dark matter, dark energy, and the initial conditions that set the universe on its current trajectory. In the realm of exoplanets, JWST's capabilities are equally groundbreaking. Its instruments will allow for the detailed analysis of exoplanet atmospheres, helping to identify potential biosignatures, such as water vapor, methane, oxygen, and complex organic compounds, that could indicate the presence of life. By observing transiting exoplanets and capturing the starlight that passes through their atmospheres, JWST can perform highly sensitive spectroscopic analyses. This will not only help to determine the composition and structure of these atmospheres, but also reveal weather patterns, surface conditions, and even potential habitability. For instance, JWST will target planets in the habitable zones of their stars, where conditions might be right for liquid water, a key ingredient for life as we know it. Additionally, JWST will significantly advance our knowledge of star formation and the life cycle of stars. By peering through the dust clouds that obscure the view in optical wavelengths, JWST's infrared vision can reveal the hidden regions where stars and planetary systems are being born. This will provide a clearer picture of the processes that govern stellar nurseries and the mechanisms driving star and planet formation. Observations of protostars and their surrounding disks will offer clues about how different types of planetary systems come into being and evolve over time. Moreover, JWST's exploration of solar system bodies, including Mars, the outer planets, their moons, and even distant objects in the Kuiper belt, will yield detailed information about their composition, atmospheres, and potential for hosting life. For example, JWST can analyze the plumes of water vapor on Europa and Enceladus, further investigating the potential for subsurface oceans to support microbial life. The James Webb Space Telescope is poised to transform our understanding of the cosmos by providing unprecedented clarity, detail, and depth in its observations. From unraveling the mysteries of the early universe and star formation to detecting and analyzing exoplanets' atmospheres, JWST will equip scientists with the data needed to answer some of the most profound questions in astronomy and astrobiology, potentially revealing new facets of the universe we inhabit. The Breakthrough Starshot initiative, launched in 2016, aims to propel humankind into a new era of interstellar exploration. At its core, this ambitious project seeks to send lightweight, sail-equipped spacecraft, dubbed starships, to our closest stellar neighbor, Proxima Centauri, which lies approximately 4.2 light-years away. Utilizing powerful ground-based lasers, these tiny probes are expected to reach up to 20% of the speed of light, allowing them to traverse the vast expanse of interstellar space within just 2 decades. The goal is not merely to reach another star system, but to capture high-resolution images and gather valuable data on the potentially habitable exoplanet, Proxima b. By doing so, we can gain unprecedented insights into our cosmic neighborhood and potentially the existence of life beyond Earth. Interestingly, Breakthrough Starshot's vision does not end with just one mission. The initiative also aims to pioneer new technologies and innovative engineering solutions that could pave the way for future interstellar missions. From refining the efficiency and precision of laser-driven propulsion systems to developing new forms of miniaturized scientific instruments, each step forward has the potential to drastically reduce the barriers to cosmic exploration. Moreover, the initiative fosters international collaboration, pooling expertise from physicists, engineers, and space scientists across the globe. This collective endeavor not only pushes the boundaries of current human capabilities, but also inspires the next generation of explorers and dreamers, rekindling the age-old human desire to reach beyond the confines of our own blue planet. Scientists have been concocting a multitude of innovative strategies to explore the enigmatic outer regions of our solar system, areas that remain largely uncharted. One of the most notable efforts is the development of the Interstellar Probe, a NASA mission concept designed to journey well into the heliosphere's outer boundary and beyond. Expected to travel at unprecedented speeds, this probe aims to reach a distance of 1,000 astronomical units, AU, 1 AU being the average distance between Earth and the Sun, within a time frame of 50 years. Equipped with sophisticated instruments, it will study the interactions between solar wind and the interstellar medium, providing unprecedented detail about our solar system's protective bubble and giving insight into the conditions that might affect future interstellar travelers. Moreover, missions like the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's New Horizons offer comprehensive perspectives on the outer solar system's intriguing components, from dwarf planets to icy moons. New Horizons, which famously captured the first detailed images of Pluto in 2015, continues to journey deeper into the Kuiper belt, a vast region filled with primordial objects left over from the solar system's formation. By analyzing the composition, geology, and potential atmospheres of these distant bodies, scientists hope to uncover the mysteries of early solar system evolution and perhaps find clues to the processes that might ignite life. Technologies such as cryobot probes and autonomous underwater vehicles are also being considered for future missions, potentially exploring subsurface oceans on moons like Europa and Enceladus, which could harbor environments conducive to life. Advances in propulsion and communication systems further enable these explorations, bridging the enormous distances between Earth and these outer realms and opening a window into regions previously shrouded in mystery. The potential for human colonization of Mars and other celestial bodies is an enthralling yet highly complex undertaking that has garnered increasing interest, particularly from organizations like NASA and private companies such as SpaceX. The vision involves establishing a self-sustaining human presence on Mars, leveraging advancements in rocket technology, habitat construction, and life support systems. One of the primary challenges comes from the highly inhospitable Martian environment, where temperatures can plunge to -80 degrees Fahrenheit, and the thin atmosphere offers scant protection from harmful cosmic radiation. Scientists are currently exploring innovative solutions, such as radiation-shielding habitats built into the Martian regolith or soil, and closed-loop life support systems that recycle air, water, and waste to create a sustainable living environment. Beyond Mars, other locations within our solar system are being scrutinized for potential human colonization. The moons of Jupiter and Saturn, such as Europa and Titan, possess unique characteristics that make them intriguing candidates. Europa's subsurface ocean, hidden beneath a thick ice crust, might not only harbor the potential for life, but also offer resources such as water, which can be broken down into hydrogen and oxygen, key components for both life support and fuel. Titan, with its dense atmosphere and surface lakes of methane and ethane, could also provide unconventional resources and opportunities for establishing human outposts. These long-term visions of interplanetary colonization involve advanced propulsion technologies to reduce travel time, autonomous robotic systems to prepare habitats before human arrival, and the development of sustainable food production systems that can function in extraterrestrial environments. While we are on the cusp of this incredible leap, it is clear that the endeavor requires unprecedented international collaboration, technological ingenuity, and perhaps a reimagined philosophy of human resilience and adaptability. Future telescopes hold immense potential to dramatically enhance our understanding of dark matter and dark energy, two of the most perplexing and pervasive components of the universe, making up approximately 85% and 70% of the total mass energy content, respectively. One of the most anticipated instruments in this quest is the James Webb Space Telescope, JWST, launched by NASA in December 2021. While its primary mission is to study the formation of stars and galaxies, its unprecedented sensitivity and resolution also make it an invaluable tool for probing the influence of dark matter in the structure of the cosmos. By observing the subtle gravitational effects of dark matter on light from distant galaxies, JWST can help map its distribution with remarkable precision. Additionally, the upcoming European Space Agency's Euclid mission, set for launch in the mid-2020s, is explicitly designed to investigate dark energy. Euclid will scan billions of galaxies up to 10 billion light-years away, meticulously measuring their shapes, positions, and movements. This massive dataset will be used to create a three-dimensional map of the universe, revealing how dark energy influences cosmic expansion over time. By examining the large-scale structure of the cosmos, including the mysterious accelerated expansion, scientists hope to uncover clues about the nature of dark energy, whether it remains constant, varies over time, or points to entirely new physics beyond our current understanding. Coupled with the Large Synoptic Survey Telescope, LSST, which is expected to generate expansive deep sky surveys, these next-generation telescopes promise to illuminate the darkest corners of our universe, shedding light on the elusive forces shaping its destiny. Sending humans to other star systems presents a myriad of formidable challenges, each more daunting than the next. At the forefront is the staggering distance involved. Our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. Current propulsion technologies are woefully inadequate for such interstellar voyages, as even the fastest spacecraft today would take tens of thousands of years to complete the journey. Thus, developing new propulsion methods, potentially harnessing concepts like nuclear fusion, antimatter engines, or even speculative ideas such as warp drives, becomes imperative. Each of these concepts, while theoretically intriguing, poses significant engineering, safety, and energy source challenges that we have yet to overcome. In addition to propulsion, the human aspect of interstellar travel introduces another layer of complexity. Extended durations in space expose astronauts to cosmic radiation, which can significantly increase the risk of cancer and other health issues due to prolonged exposure to high-energy particles. While some solutions, such as magnetic shielding or utilizing water as a radiation barrier, are being explored, these methods are still in the conceptual or experimental stages. Moreover, ensuring the psychological well-being of astronauts who might spend years or even decades in confined, isolated environments is another critical concern. Life support systems must be foolproof and capable of sustaining a stable, closed-loop ecosystem. Producing food, recycling waste, and ensuring mental health requires technological innovations and thorough testing in long-duration spaceflights. The possibility of generational ships, where multiple generations live and die en route to their destination, introduces profound ethical and logistical considerations, ranging from the societal structure of such a spaceship to ensuring genetic diversity. Ultimately, the challenges of interstellar human travel encompass a blend of technological innovation, human factors, and ethical questions, all of which need to be addressed to transform this aspirational dream into reality. The scope of these challenges underscores the need for international collaboration, substantial investment in research and development, and perhaps a new understanding of what it means to be human in the vast expanse of space. In envisioning the future of space travel and exploration over the next century, scientists and visionaries alike anticipate revolutionary advancements that could fundamentally alter humanity's relationship with the cosmos. At the core of this transformation lies the development of sustainable and reusable spacecraft, which will make frequent and cost-effective journeys to space not only feasible, but routine. Elon Musk's SpaceX has already set the stage with the Falcon and Starship series. Looking ahead, space agencies like NASA, along with private corporations, are focusing on harnessing nuclear propulsion technology, which promises significantly faster travel times to destinations within our solar system. These innovations could cut the journey to Mars from several months to just a few weeks, facilitating the establishment of permanent human colonies on the Red Planet and potentially beyond. Moreover, space exploration in the 22nd century will likely be marked by the widespread utilization of artificial intelligence and autonomous robotics. These advanced systems will pave the way for human missions by constructing habitats, mining for resources, and conducting preliminary scientific research on remote worlds before humans even set foot there. Scientists envision vast networks of orbiting satellites and space stations serving as key nodes for deep space missions. These waypoints could act as refueling stations, repair docks, and research hubs, effectively supporting longer missions to the outer planets and possibly to the icy moons of Jupiter and Saturn, where subsurface oceans might harbor life. Meanwhile, swarm robotics, clusters of small cooperative robots, could explore asteroid belts for valuable materials or even terraform planets, altering atmospheres and surfaces to make them more hospitable for human habitation. Additionally, interstellar exploration will begin to shift from the realm of science fiction to scientific reality, thanks to initiatives like Breakthrough Starshot, which aims to send tiny laser-propelled probes to nearby star systems. While human interstellar travel may still be on the distant horizon, these lightweight probes could relay unprecedented data about potentially habitable exoplanets within our galactic neighborhood. This century could also witness the advent of gigantic space telescopes, stationed far from Earth's interference, providing clearer views of distant galaxies and possibly detecting biomarkers indicating life. As our tools and technology evolve, so will our collective understanding of the universe, driving an era of unparalleled discovery and offering new perspectives on our place among the stars. What mysteries do you think lie out there in the vast universe? Could there be life elsewhere? Let us know your thoughts and ideas in the comments below. Thanks for watching.